Of Advanced Materials and Texas Tech University. His research has resulted in commercial products such as fiber-tech decontamination wipe and cotton-based, oil-based, oil-absorbent wipes. He is credited with creating technical textiles revolution in India, which played a vital role in India becoming self-reliant in developing PPE products during this COVID-19. He has received the highest award for research and academic efforts by the world's largest textile-related professional association, Textile Association India, with its honorary fellowship. He is also a fellow of the oldest chartered association in the field, the Textile Institute, United Kingdom. USA-based Technical Association of Pulp and Paper Association has given him the highest technical award in the field of non-ovens, Mark Hollingworth Prize, and the Division Leadership Award for his non-ovens work. In addition to technical research and outreach being placed in USA, he teaches Indian cultural texts to NRIs and offers lectures through many channels, which are internationally available. Most recently, he has been appointed as an honorary distinguished adjunct professor of Agile Manufacturing and Management at Chennai-based Grand Alliance of Management Excellence. Currently, he is actively involved in research related to face masks and promoting its usefulness in protecting global citizens via research and outreach. Such a resourceful personality is going to give presentation on textiles as pandemic countermeasure. We request Professor Seshadri to start with his presentation. Please, sir.
Okay, good morning, namaskar. I hope I am audible.
Yes, sir, you are audible.
Audible, sir.
It is indeed a pleasure for me to be at this conference. It's going to be deep midnight for me, but still, it's really, I'm very thrilled. I've been listening to a few sessions yesterday, talks yesterday, and I'm really thrilled that DKTE has again shown that it is an excellent institute, par excellence. So to be honest with you, it is one of the world-class academic institution, particularly for textile materials. And more importantly, I should say that right from your management, your director, Professor Kadole, your deputy director, Professor Patel, Professor Gudiavar, they are all great hosts, which people on this forum should know. Exactly 2 years back, I visited ICHALKARANJI just before I left India for United States. I never could come back after that because of COVID. But people would know that I was stuck nearly for a week because both Krishna and Panchaganga were flooding. We didn't know what to do. In spite of their own homes being flooded, Professor Patil and Gudiavar, they took so much care. And I was just really floating when I went via road to Pune, basically floating. So such is an hospitality. Of course, people can do technical things. That's not a big thing these days. But the warmthness, your institute people, particularly these people, have shown me. I have had nearly 10-15 years of connections with ICHALKARANJI. So I'm very thrilled to be there. And again, the meticulous planning these people have shown. And in fact, I have shown my I have showered my flowery recognition to Professor Gudiavar for being such a good convener and host in coordinating this. So having said that, I'm going to jump into my topic. I've been given 30 minutes. I will try to finish with that. How textiles have been known to be very unassuming. ये छोटा सा material है, ऐसा ही textile का परिणाम है. But this COVID in the past 2 years, particularly 18 months, have shifted textiles from being an ordinary, mundane, banal item that is just to protect your modesty and sometimes give fashion sense. It's kind of an elevation to the status, but now it has been really elevated to a life-saving one. Never in my life I have thought that in my 22 years of being professor at Texas Tech University, when I started research in protective materials and nonwovens exactly during July of 1999, 22 years have gone, I never thought that such materials would impact the world. So this is basically an unassuming material, but now it has become clearly a common phenomenon like Google, like Xerox, like indeed WhatsApp. Face masks have become a common phenomenon. And one of the important material within the face mask is non-wovens. And it is quite opportune and fortunate that DKTE is the only government of India recognized Center for Excellence in non-woven. So my congratulations for that. Now, where are we? Exactly a month or so back, maybe 2 months back, we thought that we have conquered this pandemic. In July of 2021, we thought that we have gotten a handle of this pandemic. But you see, there is an adage, there is a saying, there is a proverb saying the gift horse keeps on giving. So there comes Delta variant, and subsequently people are now detecting multiple other variants as well. Suddenly in the past 28 days, the infection rates is growing, and people are now seriously talking about third shot, booster shot. And with the school year, so United States starts school year a little bit late because being in the West. So school has basically begun last week. And with the kids coming back to school and campuses are all open after 18 months for face-to-face instruction, people are really worried. And now, again, debates and discussion on the use of vaccine, the third vaccination, and is there a mandatory necessary for using face masks? So this debate, charcha, has come up. So textile is in the forefront. Right now, in the past 28 days, in the United States alone, 27,000 people have died. In India, around 13,000 people have died. Brazil, around 21,000 people have died due to COVID, directly related or indirectly related to the complications from COVID. So such is the gravity. And textile materials, particularly personal protective equipment that consists of hospital items, surgical gowns and drapes, and more importantly, face masks are at the forefront. That's what it is. So even with the availability of vaccines, so vaccines are available in plenty, particularly in United States and in some sections of Europe. India is doing good, but still to a population of about 1.3 billion, it's not easy to completely vaccinate the country. Now that there is a discussion about the necessity for the third vaccination, it will take some time. Until then, face masks are lifesavers. While face masks are lifesavers, in some countries, this unavailability of unassuming products like face masks during February, March of 2020 has clearly exposed the vulnerability of lack of investment in manufacturing. So that is really boom for people in the engineering industry, that manufacturing is surfacing. Two aspects of manufacturing: advanced manufacturing and sustainable manufacturing. So rightly, this conference has been titled Innovation in Textile. One is on product. So we have to look into sustainable products. Sustainability is having different connotation. It should be first and foremost material sustainability, environmental sustainability, and economic sustainability. So sustainability is like a stool that should stand on 3 E's. My talk is going to talk about 3 E's: economic, environment, and energy. And then it is going to talk about 3 F's. F's as in Frank. One is face mask has to have 3 F's. First F is, more importantly, the heart of a face mask is its filtration capability. Second one is its fit, how it is fit to the human body, how it drapes around the human body. And the third one is the form factor or comfort factor. So I will make this talk simple, simply easy, and I will show you lot of show and tell. So I will try to quickly rush through. Maybe I will be running in the 5th gear or so. So material science, advanced manufacturing, and sustainable products are going to run the next decade. So engineers are in better position. So while we are under stress, I just want to mention and start with a positive message that engineers should be feeling proud that they are able to save lives. Okay. Now, so, and then I'm also going to give you a lot of short jargon so that you will remember. So how do we do this kind of advanced manufacturing? While I said that new products should be based on sustainability, sustainability is dependent on 3 E's, E as in English. Okay. And how do I do this? How do I develop this industry? It is based on 4 Yes. This is the technology, whether you want to wage a war against some country, whether you want to protect your country, whether you want to develop economy of a country, you have to depend on 4 Yes. First one is sensing the situation. Once you sense the situation, then you have to understand how to build things around the situation and then protect yourself or grow the industry and then maintain the industry. First and foremost, even in the situation of corona pandemic, we need to know where we are. That is sensing or analysis. So that is yes one. Yes two is once you have sensed, then you need to plan and implement. That is known as shaping. Third, once you have shaped, once I know what I have to do, what kind of machinery I have to do, you need to build around it. That is shielding, protecting. And then once you have protected and developed the system, developed the process, you need to keep on going, sustaining. So 4 Yes, 4 Yes, 3 E's, and 3 F's. That's all this presentation is. Now, taking into concept this particular protective equipment, a protective equipment like this face mask. So a face mask is there to protect. So these days people are also looking into adding additional functionality to face mask and protective clothing. So sensing, not only it is going to protect, it is also trying to sense. And then once you sense, we need to know how many vaccines are needed for 1.3 billion population, for 300 million population in United States, for 60 million population in UK. So you got to shape or analyze the situation. Once you analyze, you need to start protecting either by using vaccination or by using personal protective equipment such as face mask. And then you have to keep at it. It's not like that you just for namesake, naam ke vaste wear the face mask without proper usage of it. So in other words, sustain. Okay, so what are the types of products that can be used to develop these personal protective equipment? Any kind of textile material can be used, but depending upon the application, that's what I'm getting at. If it has to do filtration, then the primary, the heart of that particular protective equipment, in this case face mask, is a non-woven material. More importantly, a material which will have ubiquitous distribution of fibers because it has to do the job. First F for a face mask is filtration. So if it has to filter, it has to have ubiquitous distribution, not an oriented distribution. It has to have a ubiquitous or a random distribution of fiber so that it can trap particles. The particles we are talking here are somewhere in the range of 70 nanometer to 120 nanometer, particularly this virus. Coronavirus ranges between 70 nanometer to 120 nanometers. So that is the size of the particles it has to protect. So we need to have non-wovens. If you do not have non-wovens, it is better than nothing. You can have a woven material, but it has to be layered. So you need to have a layered material. So anything that is beyond your commodity fiber to fashion, just giving aesthetics and protecting your modesty is known as technical textiles. So technical textiles are not for fashion. They are not for what type of color you put, nothing. Those things are immaterial to technical textiles. Technical textiles are to provide value-added functionality. The functionality can be anything beyond the common fiber to fashion supply chain. So the technical textiles can be made, as I had alluded to, technical textiles can be made using any kind of material. Even fiber can be considered to be technical textile. Depending upon the application, it is put to. So technical textiles are value-added products that can be made from fibers, made from yarns, woven, knit, non-woven, and combination. For our particular use as a face mask, typically non-wovens are used. And technical textiles, if you need to have protection, this is the golden standard. This is the panacea. This is like Amrit going to moksha. Totally cover your body, total ensemble. Then a man becomes a zombie. So that's what I said. It may do the function, but it may not provide you the logistics. A man cannot walk. A man and a woman done in this suit cannot walk. But in certain setups where you have nuclear threat, where you have chemical threat, where you have high-level biological threat, you need to protect yourself like this. So this is called total ensemble, or known as United States Army uses this, known as JS list. That's mouthful. Joint service, lightweight, integrated suit technology. Even the name is big. Imagine, even if you are naming a product this big, this lengthy term, imagine how much technology would have gone into making this. Okay, so this is the final gold standard, panacea. Okay, uttama solution for this. So like this, textiles, knowingly or unknowingly, textiles have been used for past 30 years in many, many advanced applications. You have seen a presentation yesterday on how glass fiber composites, hybrid composites are used in wind turbines. Likewise, in every application, not knowing, if you drive a car, particularly a Toyota car and a Japanese car or a American model or South Korean model, Hyundai, in an automobile, at least there are 40 pounds, roughly around 30 kilograms of some kind of value-added high-performance textiles used, whether it's your headliner, engine filter, oil filter, insulation material. We do not know. Even your collar these days, they are not made out of plastics or they are not made out of cardboard. We will remember, people of my age who will remember, in those days we used to have collars using cardboards, and then came plastic. Now it's all, basically, it's kind of a non-woven, fusible interlining. So things have improved. That is a common commodity non-woven, but there are high-level products. And one high-level product is breathable viral barrier, BVB, and that is, the fabric is made in India. The company that makes that is Alstrom, which is a Finland-based company, but its production site is in India, in Mundra. So I was instrumental in bringing party together to get that done, built somewhere around 2006. So I'm indeed thrilled that we never had this thought 20 years back or 15 years back when I started promoting technical textiles in India. Okay, and then DKTE people came on board, and you are one of the finest centers for non-wovens in India. So now textiles can be protected. Now I'm going to quickly switch on to protective textiles, and I make my presentation simple so that it benefits the industry, it benefits new industry people, it benefits young students and even old students like me, because I'm also learning every day, that we can take home some important message. So now we know what are technical textiles, and now we are going down, we are now narrowing into protective textiles. There are 3 types of protective textiles, that's all. First and foremost is heavily dependent upon government buying, that is known as defense protective textile. Second one is medical protective textiles like face masks. And the third one, the lowest in that range, is consumer protective textiles. So defense protective textiles have high margin, ballistic textiles, chemical protective textiles. I'll show you one. This is one of the inventions that came from Texas Tech University, our lab, 15 years back. And this is the United States Defense approved chemical decontamination wipe. When there is any toxic chemical spill such as sarin or soman or sulfur mustard, this is an approved product. This came out of a laboratory, my own laboratory in Texas Tech University. So this is a high-level product. The wipe is only this much, but the product cost is high. So if you are talking about defense protective textile, the margin is high. Then comes medical, where the margin is intermediary between a defense protective textile and consumer protective textile. What is a consumer protective textile? This is a typical consumer protective textile. Your makeup remover, your hand wipe, the ordinary hand wipe, like tissue wipes, we are using spunlace wipes. I told you that I'll show you a lot of products so that people can take home, and I will even finish up with showing you an experiment, how this works. I am at my home in my dinner table, but I bought my lab, a miniature lab from my university. So this is a typical consumer wipe. So this is a consumer protective textile. And this started from your ordinary paper towel. That is a wipe, okay? Now going down into non-wovens as an important material for protective textiles. So these are non-wovens. This is a typical non-woven, cotton needle punched non-woven. So these are predominantly used. You can see that I told you for filtration, you need to have a uniform, not a uniform distribution. You need to have a ubiquitous. That means randomly distributed fibers. That is known as chaos. So chaotic representation is also useful in some application like this filtration, where you need to have that kind of a random distribution of fibers. So this is a non-woven, and most non-wovens are disposable item. That's what I said. When you are talking about next generation product, think about sustainability there, because that is going to be a big wave with all the climate change coming. So we need to think about how sustainable these disposable products are. In other words, nowadays we don't use the term disposable. These are all single use or limited time frame products, and then semi-durable. So it is the ubiquitous and random distribution of fibers. And a common form of non-woven is the melt blown. So the innermost part, it consists of 3 layers. The top and the bottom layer are spun-bond material, which are heavy and thick and more strong. And the heart or the core of this face mask is a melt blown. Melt blown is very thin. Melt blown is not strong, but melt blown is the heart of filtration because of how the fibers are arranged. And the starting material mostly is polypropylene. Like pulp is the cheapest product material, polypropylene are nothing but polyolefins, carbon, hydrogen, that's all, CH2, CH2, CH2. So these are olefin products. They are very cheap. Because we have a cheap raw material, the final product is also cheap. If we have to go and buy a product that can be used only once or twice, you will look into the cost because the volume of consumption will be relatively high. So people will obviously think about the cost. That's how this industry developed. Non-wovens are predominantly single use or semi-durable. DKTE and my lab has needle punching and thermal bonding. Okay, so these are made out of staple fibers. I'll now quickly show you why are non-wovens. Non-wovens are used because non-wovens cut short intermediary manufacturing process. There is no roving, there is no spinning. You take a fiber and then you get a fabric. So fiber to fabric without intermediary processes like spinning and weaving is known as non-woven. When you cut short the process, of course, cost of manufacturing comes down, productivity increases. You need to have high productivity to develop single use or disposable products because the volume of consumption will be high. Okay, now there are 2 types of structures which we will use. One is a staple fiber based non-woven. Needle punching is a staple fiber based non-woven. This face mask is synthetic based non-woven, whereas this wipe is cotton based, which is staple fiber based. If there are only 5 different technologies available to make non-wovens, what did I say? We started by talking about an industry. An industry depends on 4 S: sense, shape, shield, sustain. Okay, and then a sustainability is built on 3 E's: economic sustainability, environmental sustainability, energy sustainability. Similarly, the entire non-woven process can be based only on 5 different technologies. One is needle punching, thermal bonding, hydro entangling, spun melting, and then airlight. That's all. There are only 5. So I'll give you some numbers like this: 4 S, 3 F's, 3 E's, and 5 T's. T stands for technology. These 5 technologies are used to make all these products which I have listed here: hospital fabric, surgical gowns, face masks. I have underlined 3 products that are become top-notch product these days: hospital drapes, surgical gowns or PPEs, and then face masks. And this is the setup we have in Texas Tech University, which is known as needle punching. I cannot use pellet-based synthetic here. I can only use staple fibers, and commonly used staple fibers are polyester. Sometimes these days we also use polypropylene, but polyester, viscose, cotton, either in the bleached form or raw form, and sometimes polypropylene. These are the only 4 fibers that are used to develop different types of non-wovens. And if you want to develop face mask, you need to have technologies such as spun melt. Spun melt is classified into melt blowing. Melt blowing gives random distribution of fibers, and then another one is spun bond. The shopping bags you get these days, they are made out of spun bond and melt blown. There are very subtle difference between melt blown and spun bond. Let's not go into the technology. Now, what are all the examples of products you see? This is a typical blanket. I told you that I'll show you a lot of samples. This is not a woven blanket that is made in E-Road or Bhavani. This is a typical non-woven acrylic polyester blended needle punched blanket. You see the elasticity, that's the advantage. So these non-woven products have functionality. The functionality, of course, is protection, because acrylic is a synthetic form of wool. Okay, so it gives you warmth. At the same time, it gives you the elasticity. So the one the lady is having, this is the exact blanket the international airlines use. They are not made of cotton. They are not made out of woven. They are made using needle punching, using predominantly polyester and acrylic. Okay. Then you see these engine filters. And then this is a engine filter. This is an air filter in an automobile. I told you, in an automobile, there are at least 30 to 40 products. And the total weight of this is around 30 kilograms of products are used in automobile. This is a spun bond material, your shopping bag. Okay, this is a typical, India has a lot of this technology. There are about 100 such machines, and common one is made from China. Sometimes it works, sometimes it doesn't work. So the width of the machine is 1.6. All they do is you dump these polypropylene pellets. You should have seen your, you have a fine synthetic filament extruder there. I think Professor Gudiava teaches that, right? So you have that extrusion. Similarly, the same technology, instead of twisting into a yarn or a filament, you are laying into a fabric form. So that is spun bond. And this is typical pillow cover. And this is basically a carded polyester viscose blended white. So this is also a hard product now. Every time you put a vaccine jab, you know, your doctor normally swipes you up, and then he swipes you again after putting vaccine. Imagine how many, the entire global population have to be vaccinated, and 3 times they have to be vaccinated. So roughly, assuming that in 2 years, that 6 times 3 is 18 billion population, 18 times 3, right? No, 6 times 3 is 18. And each time they have to use multiple times. Assume that they are using 3 or 4 times of it. Imagine the consumption. Not knowingly, we are adding to the economy of the world. That's what I'm going to say, that engineers, particularly textile engineers, are making an impact, not only saving lives, but also improving the economy. So many different types. This is a typical spun bond, melt blown spun bond fabric, which is used in a surgical drape. But in Mundra facility in Gujarat, that is near Maharashtra, Gujarat, on the seashore border, you see this Mundra, Panoli, and places like that. You have a top-notch manufacturing facility that produces breathable viral barrier fabrics. Okay, not knowingly, non-wovens are used in so many products. This is the most. Now I'm coming to the mask, and I will show you 4 different types of masks, and then I will do one demonstration and I'll shut up. Nose clipping. Prior to COVID-19, we had a complicated process of surgical mask. There was no ear loops. People were only used to tie, majority. But in the past 2 years, almost all surgical masks are made out of melt blown spun bond. Spun bond on the top, melt blown, spun bond. And most of the time, the melt blowns are electrostatically charged. Okay, and they have ear loop. Not tying, it's very quick, ear loop, And then I told you that it needs to have fit factor. So you need to have the clip. So buy a mask that has this aluminum clip here, you see, and then you need to make it a tight fit on your nose and mouth, because the transmission route, the mode of transmission of this particular virus is airborne, and the first regions of attack are nostrils and then your mouth. Okay, second one is a surgical mask. And the third one is, now I'm going to the least one, the least efficient one is your common cloth coverings. We cannot call them face masks. These are known as cloth coverings. They should have minimum 2 layers. 1 layer, 2 layer. The layer that is next to skin should be comfortable, and the layer on the front side should be mostly water repellent. Okay, the intermediary part is, this has no non-woven in it, so the filtration efficiency is less. How do? I increase the filtration efficiency by inserting a non-woven layer. That type of face mask where we have devised and we have given a new name is known as Pfizer. A face covering with enhanced filtration is known as Pfizer. So there are 4 types of face mask. One is N95, second is a surgical mask, third one is the cloth covering, fourth one is filter enhanced cloth covering known as Pfizer. So this is your surgical mask. Okay. And the inside component of surgery, not many people would have seen this. DKT doesn't have it yet, but it will soon get it, I guess. So this is how the melt-blown webs are made. This is a typical small setup. So you could see the ubiquitous distribution of fine fibers in the range of 1 to 5 micron size. Individual fiber diameter is 1 to 5 microns. So this is the melt-blown. So the melt-blown is the heart of a surgical mask. So this is N95. And so this is what I call now a Pfizer. So this is a face cover with filter enhanced, gives you this structure. You see? But the problem is you are not able to get the tight fit because you don't have the nose clipping. But it is better than nothing. So please understand that, of course, everybody would like to use N95, no doubt about it. But in certain situations where people have gotten one vaccination, or people who have been already vaccinated, but they have some diseases, immunocompromised people, this is good enough, but this is not the gold standard. Okay, so this is what I said about Pfizer. So this is a typical cloth cover face mask with a filter insert. You see this filter insert here? So this is known as Pfizer. So 4 types of filters. Now, the other application, now I'm going to show you a demonstration, and I think I will take 2 to 3 minutes. Now, I have given you one type of personal protective equipment, which is nothing but face mask. So this COVID has developed face mask. Nobody thought that there will be any more invention in face mask. Yes, invention has happened. The face coverings and filter enhanced face coverings. So 2 products evolved in 2 years due to COVID-19. Prior to that, we only had 2 types of face mask. One is N95 and the other one is your surgical mask. Now we have face covering, new terminology came, and then Pfizer. The other product is how you take a non-woven material. This is a typical cotton non-woven material. This cotton non-woven material is manipulating the characteristics of cotton. All we thought was cotton can be only made into a denim or your underwear. But we have developed a product out of cotton way back 10 years back. All the others like Tata Fundamental Institute, BARC, all are developing now. That this is also commercial. So we take a cotton needle punched material and we show that we are utilizing the inherent characteristic of a cotton and the structural characteristic of non-woven to make a oil absorbent wipe, which is sustainable, because cotton is a sustainable product. I'm going to show you a demonstration because seeing is believing, and then we will stop. So imagine that this is a typical river or a sea. Okay, water is flowing. I cannot bring river here. Otherwise, I should bring Panchaganga here. I cannot, right? It's so far, 10,000 miles, right? So imagine that I'm going to mimic. Imagine that this is a clean water like Panchaganga or Krishna, whatever it is. I've been to Narsimhabadi. Professor Gotipamul took me. I still remember. So, right? So this is what it is. Now, into this, assume that there is a toxic oil spill. This is a motor oil. So I'll pour it and then I'll lift and show you. And I'm just showing oil poured into water so that the water system is getting contaminated, is getting polluted. Okay, I'm not doing any magic. Before your eyes, I will show you how non-woven products are. First, I have shown you how face masks are saving lives. Now I'm showing you how non-woven products are protecting the environment. As soon as I pour the oil, you could see that the water is contaminated. I hope this is visible. Most of the people are seeing, 400 people are watching. That's good. Maybe this is the only presentation in the whole conference where you will see a demonstration, I guess. Right. So now I have contaminated the water, and then I'm taking an ordinary tissue. But what happens? This tissue will sink. Whereas this non-woven cotton-based product, this was my invention 10 years back. Now it is manufactured in India. This will not sink. The material is not sinking even after agitation. And it will only pick up oil. It will separate water and oil because of the characteristics of one particular type of cotton. See, only oil, water drips. Right, watch this and watch this. It's clean. Relatively clean. See, only water drips, you could see oil. And it is already soaked up. If you take a turkey towel and put it in water, what happens? It will sink. I have already absorbed the oil, so it has become heavy. So when it is heavy, the gravity law states that it should sink, but it will not sink. It will still float because you don't need a substance that is sinking in the river or that is sinking in the ocean. It has to float so that you could remove the contamination. See, it's not touching the bottom. I am agitating like waves. See, water drifts. Now, in front of your eyes, I show you, it's totally clear. All the oil has been soaked up in this. And this is clear. That is non-woven. The structure, what did I say? The random arrangement of fibers helps to absorb whether it is a fine particle or a viscous fluid. So non-wovens play so many important. I have given you where all it is used. ONGC uses in India. And so many products. I'll share this presentation already with Professor Gudiavar so you can see it. So different types of products I have shown how one can develop. And I also publish a newsletter called Tech Snips where I put out new information like this and it is given free. So 2,000 to 3,000 people around the world from Timbuktu to Australia have subscribed. If you are interested to get this information, you send an email to me at s.ramkumar@ttu and I will be happy to add. Now I'm going to show you one more time how clear it is. So I would like to thank DKT Institute, particularly your director, your deputy director, and more importantly, the convener, Professor Gudiavar, for calling me. I came at the last minute, but I hope the presentation was useful. Thank you.
Thank you. Thank you very much, sir, for such a thought-provoking and very relevant presentation. Now we will have some questions. Dr. Ashok Rajpurohit, he has asked one question. While we have been talking of hazards from single-use plastics going to landfills and oceans, which are damaging environment and impacting sustainability, what is the world or Texas Tech doing for single-use plastics going into the face masks, gowns, and other mass-produced and used materials?
Yes, so that is an issue there. There we have to differentiate. When it comes to life-saving, you have to always give leverage, Ashok. I understand, but right now saving lives is important. So we got to take it with a little bit leverage here. But eventually, that's what I said. Eventually, all these PPE should also be made highly sustainable. I understand that's the phase of research one has to progress. But right now, the purpose is to save lives. So look at different options of disposing, whether incineration or collective disposing, or try to reuse the products. disinfect, decontaminate, and reuse. That is the next phase of works which the industry and the research organization has to collectively work together. Yes, so that's what I said. This COVID, of all the ill effects, has given us opportunity to take textiles one step ahead. When I opened it up, what did I say? Sustainable products. So we need to add more sustainability to these life-saving products. So that's next phase. Maybe for the next pandemic, I hope there is no pandemic next. But in case, we got to be prepared and then go in those directions.
Thank you, sir. One more question is there from Dr. Manas Kumar Sarkar. What I have observed that when filtration efficiency is good, air permeability is poor and difficult to breathe. Do you find any solution to solve this problem?
Yes, so we need to try what is, see, that is what important. So what is the best filtration efficiency one needs to have? You don't need to have N95. N95 is only needed. I'm only giving you, explaining in context of COVID, coronavirus, SARS-CoV-2. Only when physicians who are exposed directly to these COVID patients, you need N95. But in other situations, even surgical masks are good enough. So you got to see where, in which environments you are going to use. If a surgeon or if a pulmonologist or a physician who is exposed to this coronavirus, they need high efficiency. In those cases, you are correct. Your pressure drop will be more, so the breathability will be less. But that's not required in all the cases. So I have written many articles, even common newspapers have carried it. You need to balance. That's always going to be there. Comfort against protection. That's what I said, 3 Fs: filtration, fit, and form. Form is nothing but comfort. So you got to find where these are going to be used. If I'm going to go to a mall, I don't need N95. A simple double-layered face covering is enough. There again, comfort is a factor, but it's not as bad as N95 is when it comes to comfort. So you got to find the right choice and balance. For that only, entrepreneurs, engineers, and medical people have to put up good information. The outreach should be good. You should put fact-based information. That's what we publish in these text snips. That's a good question. So depending upon the situation, one has to handle, like everything in life.
Yeah, thank you very much, sir. One more question is there from Mr.
Okay,
Aniket
I just
Dubey.
want to show everybody, still it is floating. I didn't do anything. I was just talking to you. See, it's still floating, but this will not be the case in terms of paper or your cotton cloth. It will sink. Okay.
Yeah, related to this only, the question is whether the product shown is 100% cotton or biodegradable.
Which one? Which
oil absorbent product?
100% cotton.
Okay. Yeah. Thank you, sir. Thank you very much, sir. We request you to please stop the screen sharing.
I did, I guess.
Yeah, thank you, sir. It was a very relevant topic. As a token of love and affection.
Okay, people have asked my email ID. I have given in my slide, but you can take it. S.Ramkumar, yes as in sugar, .ramkumar@ttu.edu.
Thank you. Thank you, sir. So as a token of love and affection, we are presenting here with certificate of appreciation. We request you to kindly accept this appreciation.
So thank you. But my appreciation to, before you go, Ms. Chauhan,
yeah,
I just want to show my appreciation to DKTE. They have done a very fine job.
Okay, sir.
Okay, thank you, Professor Ram. Hello, Professor Ram Kumar. Thank you very much for a lively presentation that you have given. Okay, thank you. Now we are, Chavan madam.
Yeah. So now Our second technical presentation will be given by Professor Dr. Ayub Nabi Khan. Professor Dr. Ayub Nabi Khan is first Pro Vice Chancellor of BGMEA University of Fashion and Technology, Bangladesh. He has completed textile technology from University of Dhaka and MSc and PhD in textile technology from the University of Manchester, UK. He has received Commonwealth Scholarship as well many prestigious awards. He has 34 years of long service experience in teaching, research and in industry in different universities of home and abroad. He has published more than 60 papers in recognized journals. Dr. Khan also has worked at managerial and CEO positions in different textile organizations. He has worked as a national expert under funded project and also as an expert member in textile and R&D sectoral working committee. He has been involved in international activities like Netherlands supported CSR project, European supported RMG life cycle analysis project, German government supported higher education for sustainable textile, etc. Such a determined personality is available with us to present information on the topic research and development activities in textile sector in Bangladesh, opportunities and challenges. So we request Professor Khan to start with his presentation. Please, sir.
Thank you. Thank you. Are you going to allow me to share?
Yes, sir, you can.
Okay.
Please.
Thank you for giving me opportunity. It is a proud privilege for me to be present in this important webinar, virtual conference organized by DKT, who is one of the proud partner of BUFT. I can still remember the visit I made in 2001. So my presentation is on research and development activities in textile sector in Bangladesh, opportunities and challenges. You see, the Bangladesh is a very important destination for garments items, and it started its journey as a garment manufacturing country in 1978, and it gradually improves, and sometimes the export volume increases 3 times, 4 times, even 5 times. So we are expecting that in 2020 we would export $50 billion, but due to pandemic situation for the last 2 years, it could not be achieved due to this logical reason. Textile sector accounts for Bangladesh around more than 84% of the total revenue, and it is still growing. And recent statistics show that in this year, the export is rebounding and it is increasing due to the opening up of the business in foreign countries. Now, as far as the research is concerned, as we all know, that research is actually to do again, search to look for an development, growth, progress, and positive change in R&D, work directly towards the novelty, presenting new style and improvement of the garment's style, productivity, quality, safety, and environment. Research is the only way to achieve new level of efficiency in every operation. Through scientific work on different specific topic, ensure development of that specific part. Publication will ensure dissemination of acquired knowledge of any part of the industry to the academic and industry people. To make the textile industry of Bangladesh sustainable and progressive in institutional research and its implementation in industry can work together. As regards to the contribution of textile in our national economy, there are few areas I should mention. Textile and RMG contribute about 40% of the industry value addition, provide 4.5 million jobs, of which 70% are women. There is a huge opportunity of women empowerment. 84.21% of the total export earning come from this sector, provide 0.2 million jobs in waste recycle industry related to RMG. Contribution nearly 20% to GDP, provide indirect employment to 0.8 million workforce in accessories industries related to RMG and textile. Generate huge clientele base for banking, insurance, shipping, transport, hotel, cosmetics, toiletries, and related economic activities. As regards the vision of our primary textile and RMG industry, there are ambitious companies to expand into international market. Export-oriented RMG industry, they are saying that 58% would be has ambition to be the leading partner. In spinning, it is 43%. In weaving, 23%. Weight processing industry, they would like to be in the international market, it would be 48%. This is a survey made a couple of years ago. Yarn dyeing 74%, knitting industry 68%. That is actually the pie chart of the previous slide. A step to meet this vision of primary textile and RMG industry, the industry unit by and large are deficient in terms of skill and trained manpower. That's why we are more or less now depending on foreign expert professional in RMG and textile industry. Research is essential areas, including production and marketing. The sector will not be able to compete in the global market unless its supply of skilled manpower and research are overhauled after proper evaluation. There is a need for creating in-house research facilities due to the fact that the enterprises are in most cases large, medium, and small size. Their products are mostly on a basic nature and financially not that much capable. The lacking of knowledge on benefits of research is also there. Moreover, increasing involvement with global export business and buyers' demand has started creating the necessity for taking research support. One study shows that research facilities in textile industry, 3% in spinning sector, 1% in knitting sector, 3% in dye house sector, and 3% in RMG unit. That means research facilities available so far in these industries, very insignificant. The survey reveals that the majority of the companies, 68 to 75%, depending on the subsector, do not have any research facilities. However, about 1/4 to 1/3 of surveyed unit does find it necessary and prefer to have this support from elsewhere. The surveyed company highlighted the following areas of interest where research and development is concerned. Area of research interest in Bangladesh, the one is global and regional market research, new business project ideas, economic sourcing of raw material, product development, production planning and control, strategic marketing, improving quality and productivity, comparative study of different technologies, and sustainable product design. As you know, we have to depend mostly on the foreign raw material, especially in spinning. We nearly more than 30% of the raw cotton is imported from India, different staple length cotton. There is another areas of research interest, analyzing works, standardization of times, teamwork for friendly and new work norms, e-commerce, maintenance and replacement of machine, industrial housekeeping, labor safeguards, fire safety, women empowerment, building collapse and other disasters. There are a lot of changes happened, after the Rana Plaza disaster 2013. And Bangladesh became more or less now safe in terms of building safety, in terms of electrical safety, as per as the latest data available. There are more research can also be carried out, which is the huge prospects are there. Innovation of styles, fabric and accessories, profit margin ratio, product mix, automation, organizational development, professional development, sustainability and circular economy, efficiency and time management, and business ecosystem. Actually, you see Bangladesh is now actually concentrating, exporting only 7 or 8 items. That is that they are the basic item, we are not concentrating in functional textile or medical textile or even military textile. There are a lot of areas of textile which can be, steps can be taken by our local entrepreneurs. Primary textile and R&D-oriented educational institutions are lagging behind in promoting research and publication. There is a lackings in capacity development in education and institution, because there was only one institution, which is College of Textile Technology, but now this is became a public university, Bangladesh University of Textile, and now there are a lot of private universities like BUFT is also doing their part, and so to produce a competent human resource for supporting the RMs in textile industry. But the capacity development in terms of research is very much needed in this institution. So, and there are a few journals available for publication like ITT Journal, Bangladesh Journal of Jute Fiber Research from Bangladesh Jute Research Institute, Bangladesh Textile Today, and BUFT Butex Duet, Maulana Bashani Science and Technology University, Bangladesh University of Business Technology, and IEB Textile Division Journal. But those faces sometimes problem in getting article and sometimes reviewing. To do it in connecting research and publication in education and institution, this is an investigation of our 50 teachers and trainers. To do it in connection with their PhD and MSc thesis, say about 10%, published research work in their professional life 6%, never published any research article 84%, because there was a very little scope before. Now for the last 10 years, there are opportunity getting involved in teaching areas. But other than that, before there was industry, a lot of industry in garments and textiles. So people mostly work in industry mainly, and there was very little facilities in industry in garments and primary textile industry. So little chance was there to do research. Initiative for making capable manpower in textile sector education institution. Start research by building close link with textile industry. We should do that, maintaining a close relation with private entrepreneurs to get mutual benefits, funding offers by the enterprise on research work, and collaboration with foreign university. And as you will, you'll be happy to know that BGMA University has taken very pragmatic steps to have collaboration with foreign university. Within this 10 years time, we have started our journey in 2012. And within this 10 years journey, we have around 24 foreign university. We have a partner for university with BUFT. And I should name some of the Institute of India. One is DKTE, another one is National Institute of Fashion Technology, NIFT, which is a very public enterprise, and another one is KCT University, who has made a collaboration agreement with KCT India. Textile education nowadays is very much limited in these basic areas: yarn manufacturing, fabric manufacturing, dye printing, garment manufacturing. Fashion design is now newly started program. Textile management and merchandising, apparel manufacturing technology, knitwear manufacturing technology. But there are challenges, you know, in textile education, we have some challenges we have to face. Strong technical accreditation authority it is started, but still a lot of things to be done. Quality difference between public and private university, research and publication, not need-based course curriculum. Still there are some major overhauling needed in this area, limited practical and project works. And as we all know, the advantages of research and development, if we do carry out research and development activities in the area of in the industry as well as in the education institution, which will be a benefit for all of all the sector, especially R&D and textile. Research and development turn into knowledge, and knowledge then converted to innovation, and innovation creates value-added product, and investment will get multiple with a huge profit margin. The value-added product get performed for long-term growth and benefits. There can be a few recommendations. A special fund need to be allocated in the government budget for research work in textile sector. In private sector, BGMA, BKMA have research cell, but there should be coordinated effort with university on fruitful output in research. There is a cell there, but there is no coordinated effort between university and industry. There is scattered way of doing these things, the research. So concerted effort is needed to do effective research so that it can benefit the industry as a whole. Cooperation between education institution and industry need to be strengthened in order to create a win-win situation between both the parties by taking initiative in research and development activities. So we can be, in that case, to create a knowledge-based society, there should be a responsibility, should be the driving force. So we are working for our personal need, but it should be go to the society development as a whole, the total sector and as well as the country. So that's why I made this the vision for should be the for future world. Thank you very much for patience here, and I must thank to the DKT for inviting me in this program. I'm very much pleased, and it is a proud privilege for me. I must thank the principal of DKT, Director DKT, and the Professor Palit, as well as Dr. Satish, because we are very much close to each other. And also I should mention that one of our team has already been visited DKT and attended a training program there, our faculty member, and one semester study has been completed by our students in DKT. Thank you very much.
Thank you, sir. Let's go for the question answers. Very first question is by the participant. The question is, give important reasons for the growth of RMG industry in Bangladesh.
Yes, there is a huge opportunities there, you know, so because I should also mention that Indian NIFT students usually come to Bangladesh every year, two times they usually come to Bangladesh, and they attended different industry for doing their master's project and undergraduate project. So that can be one way. So to both together collaborative approach, BUFT and other institution of the India and other countries, we can contribute something for the betterment of our industry as well as the whole textile sector.
Thank you, sir. There is one more feedback and question also by Mr. Atik Sheikh. He is saying it is nice presentation for research as Bangladesh is developing country. Skills and mindset change research is need of an hour. This will help for positive contribution from start, mid-career professional and reduce stress of entry-level corporate and industry. Is there any plan for Bangladesh as this is big untapped area as all start from upskill and mid-set? Please advise.
Yes, I think the presentation I presented here, it shows that there is still a lot of areas to carry out, on sustainable textile, because Bangladesh garments industry is one of the main exporting destination for garments items, and we have just started some producing sustainable textile product using waste, and some spinning mills has been already been established, and also in industry there are some research going on water saving, energy sustainability, and efficient utilization of dyes, chemicals, and raw material. So these things are happening, and I think we should do more. In that case, industry and academia partnership is very much important. That means academic roles should be focused, and they should place some model for the industry, which is benefit for whole sector.
Thank you. Thank you very much, sir, for such a logical presentation. Due to time constraint, remaining questions will be shared with you and the answers we can share with the participants on the registered email ID. Thank you very much. We request you to please stop the screen share. As a token of love and affection, we are presenting here with certificate of appreciation. We request you to kindly accept this appreciation. Thank you very much, sir.
Yeah, thank you.
Now let us move ahead with our next presentation by Professor Dr. Manas Kumar Sarkar. Dr. Manas Sarkar is working as a faculty member in the Institute of Textiles and Clothing of the Hong Kong Polytechnic University. Earlier, he has worked as research head in Hong Kong-based textile company. He has completed his undergraduate in textile technology from the University of Calcutta and a master's degree in textiles from the University of Mumbai. He earned his doctoral degree in textile from the Hong Kong Polytechnic University. He has wide experience in research, teaching, and industry. He received a silver medal in the IENA International Exhibition held at Germany and the Outstanding Professional Services and Innovation Award from Hong Kong Polytechnic University. He has published many papers in various international journals. He also has international patents to his credit. Such a noble personality is available with us for presenting the topic Biomimetic approach to develop smart and functional fabrics. We request Sarkar sir to start with his presentation. Please, sir.
Okay. Yeah, can you see?
Yes, sir, it's visible.
Okay. Okay. Thank you, Chuan Madam, for your nice introduction. And I'd like to thank Professor U.J. Patil and Professor Goodyear for inviting me for this presentation. It's really nice to attach with the DKT after a long time. Yeah. So today is my presentation on the biomimetic approach to developing smart and functional fabrics. I worked in that area for a long time. So before proceed, let's see what is biomimetics. Biomimicry or biomimetics means mimicry means it's a kind of copy. So it's a copy of the nature or imitation of the nature, which has been defined as copying or adaptation or derivation from the biology or the nature. So artificial mechanism which mimic the natural ones, we normally call it biomimetics. So the natural world around us provides a magnitude of examples of functional system built with a minimum amount of materials. So that's the unique thing of the nature. So we try to grasp some of the nature's unlimited potentials to provide better solutions for smarter, stronger, and sustainable material. So here we can see a picture of the Velcro, so which is actually imitated the natural fruit bar. So imitating that bar fruit that Velcro was developed. So there are many such examples. So today we'll discuss mainly about the imitation of the nature in the textile. So why biomimetics in textile? The material developed by mimicking the nature is more comfortable because it gives you some kind of natural feeling, or it would be also environmental friendly. Most of the textiles are made from fibrous materials, and we know that nature abundance with lot of fibrous materials, and they are very sustainable in nature. And one extraordinary fibrous structure we know is the plant or tree. And our skin is also some kind of unique covering materials that covers our whole body. So if we can develop such kind of material, definitely it would be a unique thing, and we can really get some original ideas from the nature. So some of the features of the nature, like the branching structure of the nature, research already shows that branching structure of the nature assists for the quicker transportation in the plant. Uh, so not only in the plant, in the river basin also, we can see this branching structure. And when there is a branching structure, that reduce the friction and helps to transport the water faster. And unique uh, arrangement of this branching structure helps to transport a huge amount of water from the ground to the atmosphere. For a big plant, the amount is around 400 liter per day. Obviously, there are other reasons for this transportation of the water from the ground to the nature or ground to the atmosphere. But this branching structure also plays a significant role in it. Some plant leaves surface also contains special structure which made it hydrophobic in nature. So we'll talk on that also. And most plants are able to passively actuating their organs by controlling anisotropic deformation of cell exposed to the moisture. So whenever more moisture is inside the plant, the some of the organs of the plant that opens up more and allow the moisture to dissipate faster in the atmosphere. when the amount of moisture is less, it closes and reduce the moisture dissipation in the air. So such kind of things can be imitated and can make some functional fabrics. So this is a branching structure. Here you can see is the main stem, which is subdivided in the second part, and again subdivided in the third part. So it's a complete branching structure. So imitating that branching structure, we made initially a 3-layer fabric. So where in the bottom it is 4x4, either warp rib or mat. So 4 yarns are together. So in the next layer, it is 2x2 warp rib mat we can put, and in the top layer we can put a plain fabric, so it is more and more open. So in place of this rib, we can put the lino also. Sorry, we can put the lino also. So such kind of thing can make a, a, a like the main stem of the plant, and it would gives you a more compact structure at the bottom, which is completely open up at the top layer. So after making this 3-layer, we observe that water transport from the bottom to the top is very fast. But the main thing we observed that the fabric become very thick. So as this kind of fabric is more suitable for the summer, so we plan to reduce 1 layer and cut short this in a 2-layer plant structure fabric, where in the bottom layer we put 2 yarns together, which is open up in the top layer as a plain fabric. So this shows the absorption property of that fabric. So the picture is taken, the gap between the two pictures is only 0.021 second, and it can be seen that here it is, the drop is on the with the nozzle, here it is in the air, and here it is vanished. So the absorption is very, very fast. And at the top here we can see the how the 4 yarns are together, then it is subdivided into 2, and finally it is completely opened up. So for the 2-layer fabric, here we can see the 2 yarns are together and they are opened up completely in the top layer. So a similar kind of knitted structure also we have developed. So in the bottom side, we put more yarns together, 2 yarns together, and which is completely opened up in the front layer or face side. So we develop different things like using the wet knit, using the double bar warp knit. Yeah. And here in the cross-sectional view, you can see here this side is more yarns, which is completely opened up in the face side. So we observe that certain advantages can be gained from this kind of fabric. So obviously the main thing is the fabric absorbs very quickly and transferred the body sweat to the outer layer of the fabric. That means it gives you kind of moisture management property. Another thing, when it transferred to the outer layer, as the outer layer is the plain fabric, it spreads more and evaporate faster. So as it evaporates faster, the fabric dries quickly and helps to keep the skin dry. Such properties are imparted in the fabric by changing the structure. So normally what we do using some kind of chemicals we use for achieving such type of thing, but here we use it by changing the structure. So that's why it is very permanent. And such fabrics are lightweight, very strong, and dimensionally very stable. So another thing we also observed is having a very good anti-wrinkle property too. And it is also visible, means around 1.5 times more visible as compared to the regular plain fabric. So for the plant, we know when there is more moisture, the stomata opens and allow the moisture to go out easily. So we developed a fabric using different kinds of fibers. So here we use the wool fiber. Here we use the polyester fibers, and using different structure. When there is water, there is an opening. When it is dry, it is closer. So same thing we observed. This is a bit channel type structure we made. So at the bottom side, we put the polyester. At the top side, we put the wool, and a channel is made. So whenever the fabric absorbs water, this channel become completely open and allow the body sweat, body moisture to be evaporated first to the atmosphere. Another properties of the plant or tree is its leaves. Some of the plants, they have the super hydrophobic structure. So it's actually, when you see the structure under the microscope, it's a hierarchical structure. Like one microstructure is there, and on that the nano roughness is put. So we try to imitate that structure on the fabric, and you can see here we have the different percentage of the PVDF nanostructured, which we developed mainly using the electrospinning. So this is the aspect ratio, which is the ratio of the diameter and length or height. So when the percentage is higher, the aspect ratio is close to 1. But as much as we reduce the percentage of the PVDA, the aspect ratio is around 0.55 point for the 0.5% PVDF solution. So that means it gives you a sharper shape, and that shape is useful for getting a better super hydrophobicity. So we develop some dual layer structure, where at the bottom we put the bigger particles and which covered with the smaller particles, and that gives some unique super hydrophobic properties. So this is on the big particle. This you can see the smaller one. So that means similar, like micro structure initially, and on that we put the nano roughness. So using the structure, we observed some properties. Say when we use just a single layer, say from 5% to 0.5%, we saw that the contact angle of the materials is improving. So for the 5%, contact angle is much lower, and water rolling angle means when you incline the plane, at which angle it rotates. So water rolling angle is also very high. So when you go for the dual structure, means first is the microstructure, then is the nanostructure, then the contact angle comes down to around 100 55°, whereas the rolling angle comes to around 5°. But when we use the fluorinated saline molecules along with the PVDF, we can observe that very high contact angle is possible. So we can see the contact angle close to 170, and the rolling angle is only 2 or 3° like that. So using that same picture, we made a fabric where one side is hydrophobic or super hydrophobic, another side is hydrophilic. So such kind of materials are very much suitable for the bandage materials. So because it should absorb the passes all this thing from your wounds, and outside if it is the super hydrophobic, definitely would be useful for your means you can wash it no problem, without any problem. So using this stomatal structure means when the moisture is more, it will open. When the moisture is less, it will close. We develop some water responsive printed fabric. So here you can see we did some kind of printing on the this kind of cut, and when the moisture or sweat is there in the body, this printing portion absorbs that sweat, and the size of the this cut is open up. So we normally use the printing using some kind of hydrogel like EVA, PAM. Yeah. So around 50%, around 55%, yeah, the pore size is open. Another thing is the human skin. We know the human skin, water can come out from the inside to the outside, but water cannot enter from the outside to the inside. So this is such a unique thing, unique feature of our skin. So imitating that feature, we try to develop a fabric. So here is a cotton fabric. So first we coated with the PA4TES. It's a super hydrophobic material. Just we coat it first. Then we put some mask over it. It is having the holes. And then we use the plasma treatment. So after the plasma treatment, only the whole portions, it can allow the water to pass from the bottom side to the top side. And the fabric is actually a super hydrophobic fabric. From the top side, no water can go to the bottom side. Only for these portions, these holes, like the holes in our or pores in our body, the water can come to the top side. So let me show you two videos. Yeah, this is the fabric, and this is the outer side or top side of the fabric, and this is the bottom side. So this is the bottom side and this is the top side. So I'm showing you the first video. So where we'll put the water on the top side. So it is not absorbing. Now let's see the absorbing property or water behavior at the bottom side. Oh, sorry. Yeah. You can see the water is moving from the bottom to the top side. And to the top side, it rolls up. Okay, just similar like our skins. And that's all for my presentation. Any question?
Thank you very much, sir, for presentation on such a novel topic. There are some questions from the participants.
Mhm.
Mr. Atik Sheikh, he has given some feedback. Your presentation gives thoughts for going back with the nature. All worldwide sustainability agenda will be taken care. And his question is, are these innovations, which stages are they commercialized? These
Yeah.
innovations, at which stage these are
For
commercialized?
the plant structure fabric, yes, we have already sold it to a local industry. Also, when I was in the industry, we made various fabrics and we sold to Marks and Spencer, Affection, and many US brands. Yeah.
Thank you, sir. One more question is there. How to connect three different layers of fabric together in structured plant fabric, and what can be the thickness of such biomimetic branching structured fabric?
Yeah, actually, the thickness is very thin because actually we use the finer yarns, 40s count, 60s count. So yeah, fabric is extremely thin, similar like your shirt fabric. We use it mainly for the shirt materials, and we sold to means a local Hong Kong company. It's called TAL. Also, we sold it to the Marks and Spencer. Yeah, it's very thin, similar like a plain fabric, thin and plain fabric. But the big advantage is it's very much permeable because we divide the yarns in different layers. So the air permeability is around 1.5 times higher, and it's very stable.
Thank you, sir. There is one feedback again by Mr. Abhijit Weitzer. Indeed, it's a nice work and presentation. Really, it's a fascinating field. And the question asked by him is, how easy the process is to make three-layer structure? Does it require specialized machines?
No, it doesn't need any specialized machine. Actually, the yarns are interlacing from the bottom to the middle layer and middle layer to the top layer, and it itself works as a stitch. So the fabric, when you see it, it looks like a single fabric. Yeah, it's a single fabric look. Only at the back side, if you see, it gives you a 4x4 mat structure. If you see the face side, it will give you a plain structure. So it's actually a single fabric, and because of the movement of the yarn from the bottom to the top, it stitches itself.
Okay, thank you, sir. One more question, which I'll take.
Okay.
It's an innovative topic. What are the applications of skin-like fabric?
Yeah, skin-like fabric, actually, it is still in the research stage. We are working still on that. And but I think that kind of fabric would be unique for the garment materials, because that means it will keep your skin dry, and the water from your body or sweat from your body will come out to the outer layer and it will drop easily. So that would makes the garment very unique, gives you continuously a dry feeling, but no sweat on your body. Yeah.
Okay, thank you very much, sir. Many questions are there in the chat box, but due to time constraint, we will take up these questions, or we can share these questions with sir, and the answers will be sent to the participants through their registered email ID. So thank you very much, sir, for such a nice presentation on a novel topic. As a token of love and affection, we are presenting here with certificate of appreciation. We request you to kindly accept the same.
Thank you.
Thank you very much, sir. Now let's move ahead with our next presentation by Mr. Vinay Karulkar.
Namaskar. It gives us immense pleasure to introduce our next speaker, Mr. Vinay Karulkar. He is Managing Director in BWF Tech India Private Limited, Pune. He has 29 years of experience in managing business operations. He has completed his graduation in textile technology from DKD Institute. He has also completed MMS marketing from Mumbai University. He is having multidisciplinary experience with the hands-on approach to nurture an organization with limited resources. He is recognized for setting up new business units. He has successfully turned around the business from scratch twice in Indonesia and India. With this, we request Mr. Vinay Karulkar, who has showcased excellence in overcoming various business challenges, to start with his presentation on the topic innovative applications of non-woven fields in various industries. Please, sir.
Can you see my screen?
Yes, sir.
Yes.
Okay. So let me start. First of all, good morning to everyone. And my focus today will be on the real application. I'm sure you can see my slides, right?
No.
Kindly share the PPT, sir.
Can you now?
Yes, sir. Kindly go to the slideshow.
Now, can you, right?
Yes, sir.
Yes, yes.
Okay. So, what I will like to talk today is basically the application of non-woven needle felt in the real industry. When it comes to non-woven felt, we generally talk about very traditional or the applications which have been well established and we know for many, many years. Here, I would like to take you through purely onto those application of non-woven felt which are currently being used. These are being produced worldwide by multinational companies, and this I think are some of the applications which are I will say little non-conservative, conventional ones. So in today's modern world, non-woven needle felt finds its end users in various applications, and these are the one I'm talking about. And I'm not going to talk about only those applications which have been, is been just talked about, but these are being produced and it is being used globally. The first one is a filtration. Now, under filtration, there are various kind of filtrations. There's a dry filtration, there's a wet filtration. Within the dry filtration, there are various, again, subclasses. The filtration felts being used for automobile industry. Here, I'm going to talk about the felt which is used for flue gas cleaning. Take example of cement industry, or you take example of aluminum industry, copper industry, or waste incinerator, or power plants, or carbon industry. Now, these are something we kind of application which we are not heard of in textiles. But if you can imagine a big plant which is generally away from the cities, and you can see a stack where in India we call chimney, a stack, and always a gas is emitting the gases as well as the dust. And we want to filter those gases, the dust. Please understand, gas filtration is different and the dust filtration is different. So I'm here talking about de-dusting. So here what we do is that we filter those dust, and in the process, we do the emission control, right? In European countries, or especially in European countries, the emission controls are very strict. I can tell you a figure of, say, less than 10 mg per non-meter cube is the emission standard, or even less than that, even up to less than 5. And in India, we are talking about 50, and now they are talking about 30. Officially, they are talking about 30. So it means what? A lot of dust in the air, and this is the air that we are breathing. So we are using this filtration, the filters, the filter bags to filter the dust, and only the clean air is going to the stack. Then we are also using this filtration for separating solids from the liquids. And there are also industry like, as I mentioned, cement or say carbon. And these are the two industries where the product that we are filtering are actually the cement particles or the carbon particles, and we are filtering those. So what we are doing product recovery. So now what you're seeing on your screen is the 3-layer structure. The dots, the black dots shows are the dust particles. So what we have a fiber web, then we have a structure in between we call as a screen. Screen is a woven structure. So you have a fiber web, then you have a screen, and then you have a fiber web again. So it's a 3-layer structure. So what we see is a raw gas side. So imagine this is a filter media, the felt, and out of which a tubular bag is made. Okay, and that bag is hanging in a bag house. So what happens is that in this plant of cement, aluminum, or steel, the huge amount of dust is generated, and through the suction system, this dust is sucked. And on this, by using this filter media, the dust remains on the dust should remain on the surface of the filter media. The clean gas, clean air passes through this filter media to the stack, and the emission is controlled. Of course, as the more and more dust is gathered on the surface of the filter media, the differential pressure drop increases, and hence the power bill to suck the air through this fan increases. So you can have the membrane on it to do a fiber, very fine dust filtration. Sometimes you have a chemical finish or physical finish on it to impart various chemical finishes onto this filter bag. So this is the textile that we are using in the filtration. There is another interesting end use which we are using is the air slide felt. Now what you see here is a woven structure, is very stiff, around 5 mm or 7 mm. It can go up to 3,200 grams per square meter, and yet it has got air permeability. Now you have got, say, a powder product. Okay, I don't know whether you have heard of a powder called alumina. And alumina is a very fine powder, intermediate product in the production of aluminum. Very notorious dust. This dust is in white in color. It is as fine as a talcum powder, and you have to filter that, or you have to carry that alumina from one part of the plant to the another part of the plant. So what do? You can't just collect this powder. So what we use this non-woven needle felt, we call air slide felts. Okay, they may be at an angle of up to 8 degrees. And then you pump the air from the bottom. Now here, the non-woven has got better properties than the woven, because in case of woven, there is a cross-section what and where there is no air permeability. And what is the most important thing here is the air permeability, uniform air permeability. So what we do, we pump the air from the bottom, and then an air cushion is made. And on this air cushion, this powder product is transported. Very unique, but very successfully been done. This is the air slide fabric. Next, very interesting, is a fire barrier felt. The listeners from India, for your information, there are new trends coming called Vistadom or India 18 or Tejas. Now, all these trends will be fitted with fire barrier felt. So this is generally pre-oxidized, and this felt generally black in color. It doesn't burn at all. It has got very soft hand feel, and it can take any shape, any contour it can take, the shape of the seat. So you can see here, the blue color is a furnishing, the chair furnishing. Then you have got a layer of fire barrier felt. Then you have a PU foam. And why they use PU foam? Because it is very soft. It can take any shape, and it gives a comfort for the passenger. But say, for example, if you are sitting in an aircraft and if there is a fire, they say when the plane is in the air, that time you are not important. What is important is the PU foam on which you are sitting. And the moment it starts burning, it emits poisonous gases. So you want something which is soft, which doesn't burn at all, and it can take various shapes. And here it is a non-woven needle felt fire barrier, which is being used. If you travel on Lufthansa, all Lufthansa flights has got this kind of barriers on it. Next one is that, yes, we do have some miscreants, and these are all over the world. So when these people are sitting on a train and they have nothing to do, what they do, they take a knife and they try to cut the seat. Okay, and of course they would gain nothing out of it. But still, this is happening in one of the European railway, and they approached us. And what we did is that we introduced in between the layers of this para-aramide is the mesh, this high quality steel mesh. So you cannot get any cut in this. So perhaps this can be also used when you are using for wood cutting, so that by mistake, even this blades will touch, it will not penetrate into this one. So of course, this is a fire blocker, and this is what we are using on the public mass transportation system. And one of the end user is a European country here. Very interesting. Next application is this endless rollers, belts, and the pads. Please understand, whatever you are seeing on the screen is a textile material. Yes, it is a textile material. And if you see the pictures of these rollers, they do not have the ends. There is no stitching. If you see the belts here, okay, so you have a belt, and generally you have a belt, somewhere there is an ending and they do the stitching. Sometimes they have the chains also. And so you can open up and then you can have the belt. Here you have got a roller, you have got a belt, and which are absolutely endless. You have got a sealing ring, you can see the ring, and this ring absolutely have no joint. Now is applications. Now if you know the profiles of the aluminum, say like in your houses, you have seen very high-end aluminum strips being used on the windows or on the doors. And there is a big, what do I say, a mouth through which this aluminum, say sheets or say the profiles, they call it as, okay, they are extruded. And please understand, when it comes out of that complete machine, or it's called the profile itself, it is very hot. It is around 600 degrees centigrade, because the aluminum need to be given the shape. And this is such a condition that if it didn't come with the contact of any metal, there will be a scratch, and any scratch on it is immediately rejected. So the aluminum extrusion industry as such, what they want something which can withstand a high temperature of up to 600 degrees centigrade, yet they want something which is very soft in nature, so that it will not give any scratch on the profile, the material which is being extruded. So the brown is a fiber called PBO, coming from Japan. Then the yellow one, which is para-aramide, Kevlar, brand name, and then the polyester. So the moment the extruded material comes out of this machine, first it meets the PBO, then the temperature comes down to say 400 degrees centigrade, then it meets the rollers and the belts of Kevlar or para-aramide, and then when the temperatures come down to say 150, and then the polyester rollers and the belts come into picture, and then the extruded material is very gently handled, no manual touching, and it moves from the high temperature zone to the low temperature zone and to the ambient condition without any scratch. And friends, this is done by a textile material. There are n number of end users, but this is something very big industry. Of course, you also know that this there is a fiber called Dyneema, and this is the fiber which is used as one of the layer to stop the projectile, to stop the bullet. So in the bulletproof jackets, what our Indian, any army people or defense people use it. So one of the layer is a non-woven felt made of special fiber called Dyneema. Another interesting is welding blankets. And you know where it started? Koreans are very fond of barbecue. And what they do, whenever there's a summer, there's a holiday, they go on to the seafront, or like say people from Hong Kong, they will know that whenever you go to the seafront, you have the barbecue pits, okay? And then you bring your stuff and then you can do barbecue. But when you're sitting in open area, or especially in front of the sea, the wind blows, and then there will be all these fire flies, and then there's a possibility that it may catch fire. So when Koreans sit in front of the barbecue, they put something, a kind of a light blanket. Again, it is made of PAN fiber-based fiber, pre-oxidized, and it is very light in weight, up to 250 GSM or 500 GSM, as light as 250 or 200 GSM. And it's like your yoga mat. It is easy to handle, it's reusable. You just roll it and you take it to the seafront or your barbecue pit, you open it, you cover it yourself when you are sitting in front of the barbecue pit and you are doing your barbecue. So if there is any fiber, any fire being flying, you've been protected. So say for example, on the warships, there is one company in India called Masgar Dock Limited, and what they make warships. Okay, and at this stage, they tell us that anything which goes on the high seas, the choppy water, everything has to be fixed. So like if you have a desk, you have a laptop there, the laptop has to be fixed. If you have a wire, the wires need to be fixed. So in case of a choppy water, and which they encounter every now and then, and everything should be fixed. So what they do is that first the warship is built, and then the Navy engineers comes and they put on their arms and ammunitions. So they work this simultaneously, and they want a welding blanket. And then if you have a welding blanket that we have up to 500 GSM, even 250 GSM, it can absorb the sparks, but the molten metal cannot be absorbed. It makes a hole. But if you go to a thicker thickness, it even stops the molten metal. So welding blankets so far been asbestos or glass, very cumbersome, very itchy, difficult to maintain, difficult to carry, difficult to store. They have been replaced now with this kind of a yoga mat, lightweight welding blanket. Again, a non-woven needle felt. And then of course, you know this high temperature insulation material, the guy standing in front of a furnace. Of course, inside what you see is aluminum foiled garment, but inside he has got a layers of non-woven felts inside it. Another interesting, the carbon composite felts are made of viscose or pre-oxidized fibers, which are used for carbonization or graphitization at very high temperatures. And these products are used because of their properties in high temperature insulations, energy storage systems, and in motorsports. In Italy, there's a company, our customer is Brembo, and Brembo is an Italian company. For the shoe pads, they use this non-woven felts from us. So these are the very high-end applications they've been used for the energy. Say like you have huge furnaces and you want to insulate these furnaces. One of our customer is ISRO, we call Indian NASA. So this ISRO has got these communication satellites, and when the liftoff takes place, a huge amount of energy is generated, and they want to protect this communication satellite with something which will not burn and have good insulation properties. And what? It has to be lightweight. Everything goes in communication or in satellite has to be lightweight, and such kind of felts are being used there. Then traditionally, this application is undercollar. The company where I work for, 2 months ago, we completed 125 years of existence. And this company started its business with this undercollar. So you have this felt, woolen felt done by felting. So you have either pure wool, and now with the new fiber mix with the synthetic fibers, you have these undercollars or the shoulder pads. And these are the used to give a proper shape, a drape, a fall to the formal garments. Hermenegildo Zegna is one of the biggest customer. Hugo Boss, Diesel. These are the top end customers which are using such kind of felts. One more very unique applications. These kind of non-woven needle felts are being used as a sound absorber. So, like for example, I'm working with. I'm sure the students or the listeners who are in and around city of Mumbai, there is one place called NCPA, National Theatre for Performing Arts. Now, NCPA is a theater, and they have this all performers coming in, and they want something because it's absolutely a pillar-like structure, a huge structure, huge auditorium, and they want something. Let's say, for example, those Indians know a dance form called Kathak, or anyone who is having a dance performance, they have this bell of ghungroos on their ankle, and they sometimes has got such an expertise that they play only with one ghungru, one bell, and it should be heard by the person who is sitting in the last row. So there should not be any noise. If at all there is any noise, it should be absorbed. So on the walls, on the pads, wall patch, we are now going to supply them this kind of felts made with in my office. I have this ones, or like in our offices, these ladies with the high heels, when they go up and down the staircase, it makes a lot of noise. And of course, we can't ask the ladies not to wear the high heels. So what we did is that we made a frame, like a picture frame, but a frame, big frame with this felt on it, and we just put it into the staircase, and the noise gone. But like what you see in this picture, what you have, so it has got a decoration as well as you can style them, and it absorbs this one. A PVR cinema in Delhi, and there's one more theater in Kochi. They are using this felt on the wall, and they're absorbing the sound, and you can really use this as this kind of this one. Besides this, very interesting, you can use this felt for car washes. Of course, in European countries, they have the brushes, the water jet, the soap jet, the car goes in and gets clean. So whatever the brushes being used, they are made of non-woven needle felt with different colors. Of course, these felts are also used in the vehicles as interior and engine compartment. So in engine compartment, they use this felt as a lining, and so that whatever the engine compartment has got sound doesn't come into the cockpit, doesn't come into the passenger cabin. Interesting is that insole shows industry, especially for defense, they go to places where they are like farmers or sugar cane farmers, where they have this very pricky pointed this thing coming out of the ground. And here we have a shoe which is a PU sole, then we have a non-woven needle felt, and then we have shoe upper, and that gives a proper cushioning, and it prevents the penetration. You also use the felt in the steel industry, like you have got big coils, big sheets, and it has got a lot of oil and dust on it. So at the end, to take away the oil, they use a very hardened non-woven needle felt. It's very hard, but it's a non-woven needle felt, and it is used to scrap or take away the oils and the dust which is on the surface of this one. I think this is something which I wanted to talk today. Of course, this is a very big, very big subject, very vast, and a lot of things been happening. We are using, and this has been industrialized. It's been used, it's been produced, and it is being used regularly in the industry. And this is what I thought I should share today with you. If you have any questions, you may ask.
Yes, sir. Thank you. There is questions from participants. The first one is Priyam Shah Patel says, what is the commercial cost of fire barrier felt fabric, and what is the raw material used in manufacturing the same?
The price not so expensive compared to compared to the function age case, you can get it up to say 1,000 rupees per square meter, up to that. And of course, as I mentioned, these are the PAN based fiber, pre-oxidized fiber.
Okay, sir. Thank you. The next question is by Abhijit Weitzer. He asks, does this felt have use in aluminum smelting industries, and which kind of fiber blends are being used to make it?
Yes, it is used in aluminum smelter, in FTP, fume treatment plant, or it is called GTC, gas treatment center. And this is where the huge amount of dust is generated. Generally, looking into the temperature it has, polyester is used. But polyester with a very special chemical finish is called alusurf. So it has got very special finish on it because the dust which it emits is very abrasive. It can tear off the polyester, the bag itself.
Okay, sir. Thank you. The next question is by Dr. Manas Kumar Sarkar. He asks, in recent years, CNT sheets are used as bulletproof, which is lighter than aramids. Have you tried such materials?
Yes, people are using it. People are using it. Our customers who are using this one, they are using it, but they want, see, anything which goes in defense as a protective wear for the soldier, they want everything light. And that's the reason they are using this Dyneema, which is around 200 or sometimes 300 GSM, depending upon the V50. So yes, it is being used, and now this non-woven felt being used regularly.
Okay, sir. Thank you so much. The remaining questions will be shared through mail. Due to the time constraint, we will go ahead. Sir, thank you so much for your stimulating speech. As a token of love and affection, we are presenting here with certificate of appreciation. We request you to kindly accept the same. Please, sir. Thank you, sir. Now we will have next presentation by Mr. Martin Pulzer, who is working as associate at the Institute of RWTH Aachen University, Germany, in the Multi-Filament Technology Department. He has completed his graduation in Mechanical Engineering from RWTH Aachen University, specializing in plastics and textile technology and business administration. The focus of his research is on the development of melt spinning press process for hollow fibers. Mr. Pulzer carries out research on the melt spinning and the fiber post-treatment, as well as on the analysis of polymer and corresponding fiber properties. Such a diversified personality is going to kindly, I request everyone to mute their mic. Such a diversified personality is going to present information on the topic melt spun poly4 methyl pentane 1 hollow fibers for gas separation applications. We request Mr. Martin Pulzer to start with his presentation. Please, sir.
Yeah, thank you for the introduction and for the invitation to this conference. I'm sharing my screen. Hope everyone can see it.
It's visible, sir.
Oh, perfect. Is it full screen mode?
Okay.
Perfect. Okay, welcome everyone to my today's presentation, melt spun poly4 methylpentene hollow fibers for gas separation applications. So my name is Martin Pelzer, and I'm going to present you the research results of a joint research project between the ITA, the Institute for Textile Technology of RWTH Aachen University in Germany, and the AV Topchev Institute for Petrochemical Synthesis, shortened TIPSRAS in Moscow in Russia. So a brief words about our institute. So we have roughly 100 scientific research associates at the institute, are mainly focused in textile machinery, textile processes, in material and polymer modification for fibers, and also in the simulation of textile processes, such as weaving or the texturization process. We have a big machinery park, go from the material, from the raw polymer over the filament fabrication to the textile fabric, and then to the textile product. And you see the textile chain here, from the material over functionalization to the products, mainly technical textiles. So we are active in different sectors. In the automotive sector, for example, airbag development or seat cover development, building and construction. So for example, fiber reinforced concrete, information and communication. So smart textiles, sensor actor technology, energy and health. We are active in artificial stent research or tissue engineering, and in the home and living sector. So we carry out our development all over the textile chain. Here are some examples. Optics, we develop optical polymer-based fibers at ITA, for instance. Electronics, as I mentioned, sensor actor technology. Additivation, we functionalize fibers for drug delivery in medicine, agricultural fibers, and abrasive fibers also, and antibacterial fibers. So all the functionalization of fibers. And we are carrying out research on sustainability. We develop melt spinning process for bio-based polymers, starch or PLA, for instance, or PHB. We are active in texturizing processes, ATY and DTY. The digitalization of all the and the interconnection of all textile processes, and different spinning processes, from melt spinning to bicomponent or even three-component filament melt spinning processes, but also solution-based spinning processes, and in the development of hollow fibers. And this brings me to my topic of my presentation today, the hollow fibers for gas separation. So here I have two examples where hollow fibers are actually used to separate gas mixtures. And one example is the biogas conditioning, where methane from butane, from CO2, sorry, have to be separated. And then the natural gas conditioning, where methane and butane are to be separated. How does the separation work? The gas mixture, so different hydrocarbons here, come into the fiber. One component passes the fiber wall and is removed outside here. This is called the permeate. And the other component remains in the fiber and is removed at the end of the fiber. It's called the retentate. So conventional hollow fiber membranes are solution spun. But we don't want to solution spin the fibers. We want to melt spin them because it's more ecological and more economical. We just melt up the polymer in the extruder over different heat zones by a screw, extrude the melt through a spin pack, and go to the winder. But via this process, we only receive a precursor for membranes. We need to post-process the obtained fibers in the second step. This is the so-called crazing. This could either be a cold drawing or hot drawing. We can anneal the fibers or draw the fibers in an organic solvent, or we can perform a combination of all these processes in order to obtain a dense selective layer, in order to decrease the wall thickness of the fiber, and so to decrease the diffusion ways of the gases. And also we want to maintain the fiber to be textile processable in further steps. For example, to manufacture knitted or braided fabrics from the fiber. Our goal geometry of the fiber is an outer diameter of between 120 to 150 microns and a relatively thin wall thickness of roughly 10 microns. So at first I'm going to present you the material, the PMP I used, then the melt spinning process of the hollow fibers, the permeation measurements we conducted on the lab scale module on a precursor of these fibers, the subsequent crazing process of the hollow fibers, and then the textile module manufacturing. And then I'm going to give you an outlook about the textile module testing. So which polymer did we use? We used polymethylpentene, shortened PMP, from Mitsui Chemicals in Japan. This grade is called TPX MX002. PMP is a thermoplastic aliphatic polymer with a glass transition temperature of roughly about 30 degrees and a melting point of quite high of 225 degrees due to the large side chains of the polymer. And the density is quite low. It's one of the lowest polymeric densities of roughly 0.83 grams per cubic centimeter. The crystallinity degree can reach up to 90%, depending on the drawing ratio you apply in the spinning process and depending on the post-treatment. And the PMP is very high. This is a big advantage, a very high resistant against C3 plus hydrocarbons, which makes it attractive for the separation of hydrogen sulfides from oil, for the separation of different hydrocarbons from each other, and for the CO2 separation from various industrial process streams. So the melt spinning we carried out at 2 different lines. On the left-hand side, this is the larger line, capable of 500 grams per hour. We melt up the polymer, pressed it through the spin packs, and then directly went to the winder. And the smaller line, capable of slightly below 100 grams per hour, we went to a water bath with 4 hollow fiber filaments, and then went to the winder without any further post drawing here. We used 2 different spinneret concepts to produce the hollow fibers. Spinneret concept 1 was the pilot melt spinning plant you have seen on the left-hand side. Here we used a 2 C-shaped nozzle with 10 holes. One hole is concepted like this. This is a C, this is the other C, and the air comes into the fiber directly after the extrusion through this gap, and then down the extrusion direction, the fibers close, and we obtain a hollow fiber with this supporting air in the core. The spinneret concept number 2 for the lab scale melt spinning plant. Here we used a full profile spinneret with supporting air in the core, atmospheric pressure, with 4 holes in total. You see here the geometry, slightly below 1 millimeter in diameter and outer diameter. And then here in the center, we have the supporting air that we get into the fiber through the spin block. Here you see the results from the 2 C-shaped spinneret. At first, we had to figure out which spin head temperature is suitable to produce hollow fibers. And here you can see at 270 degrees, the fibers don't connect. The 2 C's don't connect in a sufficient way. And while increasing the temperature, the results become better. And the best temperature here is 290 degrees, where we obtain sufficient hollow fibers. So here we have identified the process window for producing hollow fibers from the PMP regarding temperature, the outlet area, specific throughput, and other important spin parameters. And here you can see also an effect of the drawing speed. You can see here, if we increase the drawing speed, the winding speed, the fibers, of course, become smaller. And these diameters are far out of the target range, because we want to aim for 150 microns in outer diameter. Here's a comparison from the hollow fibers we obtained from the two concepts. On the left-hand side, the two C-shaped spinneret, winded at 500 meters per minute, spun at 290 degrees. And on the right-hand side, you see the much better fibers, spun at 280 degrees at quite low production speeds of 25 to 40 meters per minute, with the supporting air in the core. Using the spinneret concept with the supporting air in the core here, the spin head temperature has the biggest effect on the fiber geometry and the cross section. So on the left-hand side, you see fibers spun at 280 degrees, so quite thin-walled, and while increasing the temperature by 20 degrees, the hollowness decreases, and these fibers are not hollow enough for our application. And as you can see here, both fibers spun at 25 meters per minute. What is the effect of the production speed? This on the wall thickness, this you can see in the diagram on the left-hand side. The wall thickness is depicted in independence of the production speed. And what you can see here is that the wall thickness significantly decreases when increasing the production speed from 25 to 40 meters per minute. And at production speeds larger than 40 meters per minute, there is not a significant effect on the wall thickness anymore. And we think that here, the supporting air still has an effect in the fibers, and at higher production speeds, the supporting air loses its effect. At low production speeds, the outer diameter becomes smaller, while the inner diameter stays about the same. But at higher production speeds, both diameters decrease. This is on the left-hand side a light microscopy image, and on the right-hand side an SEM from the best hollow fibers spun at 280 degrees and 25 meters per minute. They have a crystallinity degree of 36% because they are not drawn that fast. And here I want to give you a comparison between both spinneret concepts. On the left-hand side, you see the hollow fibers obtained from the two C-shaped spinneret with the 10 holes. The crystallinity degree is quite high, about 50%. We could manufacture the fibers at quite high production speeds, up to 1,000 meters per minute. But the fiber diameter is too small for our application, and the hollowness is not large enough. The concept 2 with the supporting air in the core is the best concept so far. The fiber diameter is in the target range of 150 microns. The hollowness is large, but the drawback is that the crystallinity is not that high, and the production speeds are quite low. You remember 25 to 40 meters per minute compared to this 1,000 meters per minute. We manufactured a lab scale module from our best fibers, spun at, not from our best fibers, but from fibers from the supporting air spinneret concept. you see this lab scale module here, the fiber cross section, the sealant, which is the potting at the end of the fibers. So we took 150 pieces of single hollow fibers, potted them at the end, cut them to have open fibers here, and then manufactured this lab scale module for the gas separation measurements. We carried out bubble tests at the module in order to check if the fibers themselves and also the potting is gas tight, and determined separation factors of around about 6 while measuring methane and CO2. This is quite sufficient, and the bubble tests showed that the fibers are gas tight. What are the results of the permeation measurements? I don't want to bother you with this topic too detailed, but we have measured the permeability Q on the y-axis and the dependence of the reciprocal temperature 1 divided by T, which means the farther you go from the left-hand side to right, the temperature decreases. So here 0.0033, this is around about the glass transition temperature of 30 degrees. And what you see here is that the permeability have Arrhenius character, and that the permeabilities are not sensitive to the glass transition temperature here. So the cold or the the colder the temperature or the lower the temperature, the lower the permeability Q. And these results are comparable to the permeation behavior in PMP films. What is interesting is if you look at butane here in blue, butane compared to methane in red, methane has Arrhenius character in the permeability, but below Tg, the permeability of butane increases very rapidly compared to that of methane. And here you can say that below the glass transition temperature, the membrane turns from a butane selective into a methane selective one. So very large differences in the permeability Q. What about the post-treatment of the fibers? You remember the goal was to obtain a dense selective layer, to decrease the wall thickness and to increase the selectivity for C2 to C4 alkanes through the fiber wall. At the same time to maintain the textile processability. This we carried out by drawing the fiber in order to obtain these micro crazes. How did we do that? We manufactured the device, a lab device, in order to clamp the fibers, to put the whole device into a light solvents such as acetone or butanol or isopropanol. And then we could draw the fibers in the bath, the fiber bundle. This is the design of experiments. We carried out the drawing trials in different environments, in air as reference, in acetone, isopropanol, and butanol. Applied different post-drawing ratios, 20, 40, 60, and 80% each time. And then we choose 2 different exposure times. So either we directly removed the fibers from the solvent after crazing, and at the other trials we waited for 30 minutes in order to give the crazes time to grow. And we had a bundle here. which was clamped at the fixed end, and then via this thread rod we could move the other end to apply the drawing. And we had a fiber bundle in order to have enough material for the light microscopy, for the SEM, and then for the DSC measurements, because we wanted to determine the degree of crystallinity. Here you can see the crazing results from this lab scale module, which we of course did discontinuously. We just draw the fibers and then remained the fibers in the solvent. This is the untreated reference. And then after crazing for 30 minutes, drawn by 60%, we obtained such a quite porous morphology here with in radial fiber direction with such lamellar structures, which are quite promising results for the application in gas separation. Then we carried out the drawing continuously between heated goddets, either at room temperature and at 80 degrees. Here we applied the drawing ratios between 20 and 280%. Then to the second goddet, we had a negative drawing ratio due to the shrinkage of the fiber. And then we went to the winder to have yarn tension here. We used a drawing ratio of 6%. What you can see on the right-hand side is that 100% is a reasonable upper drawing ratio to maintain the fibers hollow at large drawing ratios of 280%, and even at 200%, the fibers become damaged, and you see they heavily deformed and they got blocked. So you cannot use these high drawing ratios here. These are the morphologies after crazing in acetone. You have seen such a picture 2 slides before. And then the morphology after the continuous drawing at room temperature by 100%. And if you compare this to the untreated reference, you see that even at the continuous drawing, a porous morphology has been built. What did we do with the precursor fibers? So with the untreated hollow fibers, we manufactured textile modules from these fibers. We used triaxial braiding of advanced textile modules, and also a tape weaving technology. So for the triaxial braiding here, you see the manufacturing of a tubular module structure for improved gas flows. So the textile structure actually has the function of a spacer in the gas separation by the undulation of the hollow fibers. And the hollow fibers can be used as a spacer. The tube diameter was about 1 centimeter, and we carried out trials with 24 PMP hollow fibers as standing threads, and as braiding threads, we either used 24 or 48 monofilaments with the same fineness. We varied the braiding angle from wide, medium to small. So at the end, we had 6 different fabrics here. Then we manufactured a woven tape from the hollow fibers, where we used as the hollow fibers as weft yarn. As warp yarn here in this direction, and as weft yarn, we used the PMP monofilaments as dummy filaments. We used different bindings, twill and atlas, and varied the weft density from 6 to 10 and then to 15 per centimeters. So in this case, in the tape weaving case, we also had 6 different fabrics at the end. As an outlook, I want to tell you something about the testing of the modules. So here you see a metal testing module where the textile modules are applied to. You see here the inlet of the feed gas and then the outlet for the permeate and the retentate here. And we have sent the textile modules to our Russian partner for the further testing. And we haven't received the results so far, but I'm expecting the results within the next weeks. And I'm quite curious about the performance of these textile modules. To sum up my presentation, or the most important results, we have identified a suitable melt spinning process for the hollow fibers, and here identified this temperature range as suitable. This is quite high compared to the melting point of 225 degrees. The full profile spin rate with the supporting air in the core, atmospheric pressure led to the best hollow fibers and to relatively thin-walled hollow fibers with an outer diameter of 200 microns. And we could create porous morphologies by the discontinuous and also by the continuous drawing at room temperature and under air atmosphere. Yeah, we successfully manufactured lab scale testing modules based on the untreated hollow fibers and characterized the gas permeability and the gas separation properties. For CO2, methane and nitrogen, we could determine a temperature-dependent permeability, which was not sensitive towards the glass transition temperature. And below the glass transition temperature, this was the most impressive result. We determined that the PMP fiber membranes turned from the butane selective into a methane selective membrane. And at the end, what I presented at the end, we showed that we could manufacture advanced textile modules from the untreated fibers by triaxial braiding and by tape weaving technology. And at the end, I want to thank the Russian Science Foundation and also Deutsche Forschungsgemeinschaft for funding this joint research project. And I also want to thank Mr. Tukov from Tipsaras for manufacturing the membrane modules. This brings me to the end of my presentation. I want to thank you, and I'm looking towards your questions. Thank you very much.
Sir. Thank you so much. The participants' questions are here. The first question is from one of our eminent speaker of conference, Professor Nico. He asked, have you ever tested the influence of different additives or nucleating agents to influence hollow formation, diameter, and other properties of your hollow fibers?
Yes, we have done that. We have additivated the PMP, but we have to carry out the melt spinning trials with the additivated material. We had used nucleating agents for the PMP. Mainly silica particles concentrations, roughly about 0.5% weight percent, but we still have to spin the fibers from this material in order to increase the crystallinity.
Okay, sir. The other question is from Mariam. He says, thanks for nice presentation. And he also asks, what is the role if we use hollow nanofibers instead? And what are the benefits and limitations?
Sorry, again, you mean nano hollow fibers?
Hollow nanofibers.
Yeah, these are not nanofibers. We don't want to produce nanofibers. We want to obtain filaments as large as possible. So in the range of 200 microns in diameter, not nanometers, not microns. because we want to contact the fibers and do the filtration from in to outside the fiber. And we don't want to use particle separation, as you know, from nanofiber nonwovens, for example. We use the fiber as membrane here for gas separation, not for particle separation, but for ultra and nano filtration of gases.
Okay, sir. Thank you so much. We are pleased to have your participation in this conference, sir. So as a token of love and affection, kindly accept this appreciation certificate. Thank you so much.
And thank you so much.
Thank you, sir. Now we will move ahead with the next presentation by Professor Dr. Parikshit Goswami. Before that, would like to have one announcement, sir, that feedback link will be posted in chat box during the valedictory session. Participants are requested to fill and submit it for e-certificate as well as conference literature PPTs. Now, next technical presentation by Professor Dr. Parikshit Goswami. We will like to introduce him. He holds MSc and PhD degree. He is the Director of Technical Textiles Research Center and is the head of Department of Fashion and Textiles at the University of Huddersfield, UK. Earlier, he worked as the Director of Research and Innovation at the School of Design, University of Leeds, and he headed the Fiber and Fabric Functionalization Research Group. His domains of research are product development using flexible materials and application of chemistry for functionalizing textiles. He manages a large profile of research concerned with polymer science, nonwovens, medical textiles, and many more. He is a member and trustee of Society of Dyers and Colorists, Education, Qualifications, and Accreditation Board, and is a member of IRANA's R&D Working Group. With this, we request Professor Parikshit Goswami to start with his presentation on topic invention, innovation, and the value of depth. Please, sir.
Sure.
Can you see my presentation?
Yes, sir. It's visible.
Good. Right. Thank you very much for that kind introduction. Can I request one thing before I start? Means
Yes. Yes,
people feel free to keep your camera switched on. Means during COVID times, we are talking to blank screen all the time. So if you are comfortable, please switch on your camera. I'd like to see my audience if possible.
Yes, sir. But then
no, because of certain technical issues, the videos are put in the off mode, sir.
Not a problem. I like my face, so I'll look at my
face.
It
is. I think we are very much comfortable with you, and you can start. Sir.
Not a problem.
Okay.
So, thanks for that introduction, and to kind of articulate what I do internally in my organization, University of Huddersfield, but externally, I'm also involved with a lot of initiatives. One was mentioned, SDC, where I'm a trustee and EQAB board member, but I'm also a board member for UK Fashion and Textiles Association, with almost every retailer and manufacturer in UK involved with that. I'm also a board advisory board member of Textiles 2030, where we are trying to guide the UK textile industry to achieve its sustainability Paris 2050 targets. So what I'm trying to do today, it's trying to take you through my understanding of innovation, what I have learned over last few decades. Means that is what I'll try to talk today. Now, the biggest understanding that I got is the popular view of innovation, where a slightly weird looking guy doing very funny and weird stuff is actually not the reality. The reality is very different. In reality, there is no eureka moment. Research and probably innovation and invention are absolutely about how disciplined you are, how strategic you are. It's about rigor, it's about novelty, and it's about understanding how to do research. And I want to share some of that experience with you in this for the next, hopefully, half an hour. So to understand innovation, we first need to understand what the term means. There are two terms which we discuss a lot. One is called invention, the other one is called innovation. Are they synonyms? What is the difference between them? So invention is just creation of the new idea. That's it. You have an idea, and that's invention if it is novel, right? However, to make it innovation, you need a strategy for exploiting that idea. So innovation is the bigger picture, which means innovation is invention plus exploitation of that idea. Means my previous speaker, Martin was presenting about hollow fiber, and you can see that invention is when probably Martin thought that I'll do some hollow fiber for this application. But for innovation, Martin has to go through that serious rigor of research. So successful innovation is defined as a process whereby new ideas are transformed through economic activity into sustainable value creating outcome. That is innovation. Publishing a scientific paper is not innovation, it's invention. Innovation is where we need to interact with the wider world. Innovation is not just an idea. Innovation is achieved when idea is transformed into an outcome which got value. And that is really the important thing. So application, and that is where I will target my discussion today a bit, and I'll explain why I'm doing it. I genuinely believe, and there must be many students who are attending here, innovation is not always a rocket science. Anybody can do innovation. My profession is to do innovation, right? That is what I get paid for. But the biggest, and I'll show some of the work I have done, but the innovation that I was most fascinated with was not rocket science, was this. Means for my sins, I have to go to a lot of dinner parties, and we used to struggle holding the food and drinking at the same time. Somebody somewhere thought about it. We all did, but they solved the problem. Brilliant, serious innovation. Not really a very big invention that can be published, but a seriously good innovation. Somebody somewhere made a lot of money out of it. And that is what we need to blend into our scientific research, creativity, which is the most important human resources of all. And when we do that, innovation and nice things happen. Take another example. It is about observation skill and understanding the consumer needs. I'm a big fan of this guy, Steve Jobs. He never invented computer, but he made it user-friendly, genius, and made some money out of it and have a world-leading company. What I want to do in the University of Huddersfield is, apart from developing the scientific skills, I want to cultivate that skill into students, where they are interacting, where they are observant of the wider world, which is really, really important. What happens in universities, and we are all guilty of that, right? We did do a lot of research, basic fundamental research. We are good at that. We publish that. My interest is what happens after that. Do a significant proportion of our basic research converts into applied research and eventually into a product? I must say we are guilty. We are guilty as a higher academia infrastructure of always not doing it to best of the ability. It will never happen that we'll convert 100% of our basic research into a product with a plug in it. But we should do better. And therefore, my discussion today is not really how to do it. It is methodology, and I have given enough of my published papers and probably a few patents here so that if you want to read methodology, you can go back and read it from my papers. What I want to discuss today is what to do research on. That is where leadership comes. That is where leadership, for example, as director of Technical Textile Research Center and head of the Department for Fashion and Textiles, I have to show some leadership to channel our research, our limited resources, into something that got value. And that is the skill, unfortunately, we really don't teach even at a PhD level. We always teach how to do the methodology, how to do research. And therefore, what to do research on is a really important inquiry for me. And it is a factor of leadership and also personal aspiration. My personal aspiration is sustainability, circular economy, so on and so forth. And therefore, I do research which is slightly targeted towards that domain. Not that always I do that, but we work with many companies, and I'll give you an example of one project. But that is always the underlying tone of what I try to do. For example, I did a project with, I think with Malaysia in this one, where we developed a recycled fiber based on carpet waste. So we actually, it came to our attention that a lot of plastic carpet waste end up into landfill. So we made some collaboration. We created a multinational consortium. And in a way, this research is not too dissimilar to what Martin was presenting before. But we take two different polymers. We very thoroughly model the interaction between those two polymers that are in normal carpets. And we created some fibers with very defined pore structures. And we tried to map out, to model the process parameters, the starting material with the pore structure, so that this can be used for filtration. At this moment, we are trying to exploit some commercial routes for that. But what is the vision? The vision was, we knew that there is a serious waste problem, which ends up in the landfill. We tried to upcycle that waste into a product that has higher value than that waste. Now, similar kind of technique where we are trying to understand how two materials interact with each other chemically is used for other projects. For example, this is one patent that I got with Adidas to produce sporting goods. Now the concept, the scientific concept that is used in these two projects are not million miles apart, but the application is very different, and both the applications got commercial market associated with that. That in our term means impact. Our research will have some impact. Now, can we do all the research on our own? Means let's take a step back and accept the fact that we are textile scientists. So many of us in this forum have spent not years but decades learning our skills. Now there is no way I'm going to learn another skill in much more details, and that is where the modern direction of travel comes, where we are talking about disciplinary boundaries. We start doing multidisciplinary research where we bring different elements, say biology and textiles, closer together. Then we supervise PhD students who becomes interdisciplinary expert. What is interdisciplinary? Interdisciplinary is where the boundary between different disciplines got porous. You have expertise which kind of cuts across different disciplines, with the ambition that eventually it will be transdisciplinary, where the boundary between different disciplines will not exist. We will create expertise with our students who will know textiles and biology in equal measure, and they can have some serious impact in the world. And once you start practicing that, the world is your oyster. Means you can do medical textiles, construction, horticulture, architecture, you name it. Today, I'm going to give some examples of medical textiles, but that is not where you have to limit yourself. You can actually learn a skill. You can blend that with your passion and do something that is really novel and nice. You can even use it for artistic output. And if you think I'm making it up, then this is a news article published in what is the name of the paper? I forgot now. But one of the leading news outlets, The Guardian, in UK, and it published where I collaborated with a sculpture artist. I was developing artificial skin, and I collaborated with the sculpture artist, and we do something really, really exciting, which was presented in one of the biggest art galleries in UK. So it can be done. But let's come back to our normal business, medical textiles, which is such an exciting area to work on. It is evolving on a daily basis. We know the importance of that during COVID. And you can do so much in that area. You can develop simple wipes to tackle hospital-acquired infection. You can make complex structures for bone replacement. And I'll give you one example of that we are doing. So the areas are implantable material, where, say, artificial ligament, we implant into the body. Non-implantable material, I'll give one example of that. Hospital environment material, which is surgical gowns and face mask and all sorts we learned during COVID. Now, I am not giving too many examples of healthcare environment material today, though that is one of my active research area. I'm not doing it because I thought I can talk about it another day. It's only a kind of half an hour presentation, so I left it out. And I'm giving some case studies from my group. Before I go there, mainly to the students who are attending this, try to understand the difficulty of this research. Because we are textile engineers and textile scientists, we know what to do with textiles, but that is unfortunately not enough for this kind of research. We need to collaborate with other people. We need to understand how cell cultivation happens, so on and so forth, cell migration happens, and therefore it is about collaboration. And collaboration is a skill, is a transferable skill that you need to learn. It don't come automatically. And there are a lot of governance around it. So I want you to at least have appreciation of that. So a few case studies, right? The first one is ostomy pouch. What is that? People who have bowel cancer, and there are a lot of them in Europe and in the UK, their large intestine is taken out of their stomach. So what that means is they can't participate in normal toilet activities. The human waste can come out at any time from their stoma into a bag, which is known as ostomy pouch. It happens as a result of bowel cancer and other things. And this problem is one, financially demanding, and the second thing is this problem is increasing. There is a lot of bowel cancer cases, which is increasing. People are living longer, so this problem is growing. What is the problem with it? Now, see, if a person got a stoma, they used to do normal toilet activities. Now, once they have the stoma, the human waste is coming out through a bag at any point. They might be at their office, or they might be at a relative's place where they have to remove the bag, put it in a normal bin with human waste. That got huge psychological implication for the people. Environmentally, which was really something I wanted to tackle, this human waste ends up in the landfill. In fact, in the UK alone, this is 2014 figure, where 36.5 million stoma bags end up in the waste. They have things like hookworm and tapeworm, which remains in the environment for 10 years. And facial contamination can give you a lot of disease. We know that. So somebody came to us, a company, and said, if you can develop a fabric, now hear it out, which is super hydrophobic, but disperses in water, then we can solve the problem. Technically, it was difficult to achieve, but this is what we did. As you can see, the fabric is super hydrophobic. But when you put it in excess of water and give a given amount of mechanical agitation to that sample, a predefined amount, it disperses into single fibers which are biodegradable. What that means? That means we can make an ostomy pouch out of this material, and then the patient can just go to the toilet and flush the whole thing out. And our infrastructure can take care of the human waste, which will have huge implication to the environment as well as the psychological aspects of the patients. And we are in a process to commercialize it. Now, from there, come to a real problem. Another problem where you must have heard of chronic kidney disease, which is if you have a chronic kidney disease, you do a process called hemodialysis, where the toxins, there are 150 kinds of urotoxin, which is in our body and which kidney filters, known toxins 150. We use an artificial filtration device to remove that from our body. Brilliant. What is the problem? The problem is the water-soluble molecules can be removed that way. The middle molecules, dialysis is not that good with. Protein-bound macromolecules, dialysis just can't remove. That builds up in your body. That can give you all sorts of things like cardiovascular disease. But to have a treatment, you need a kidney transplantation, because otherwise dialysis can't do that. So we developed a process where we added different actives into the fibers so that we can remove targeted toxins from the blood. And we are doing a lot of research on that with the ambition that eventually it will give a solution to chronic kidney disease, which don't end up with kidney transplantation. And it can be done. We have huge amount of textile literature, which we can inform this research on. We are collaborating with clinicians, we are collaborating with biologists, and we are trying to solve a real health problem that otherwise can't be solved. Similar kind of technology can be used for creating antimicrobial agents. For example, in this research, we have used a natural ingredient. This is NMO, methyl glyoxal, which is in Manuka honey. And we did some scientific work to encapsulate that into textile fibers. And then we have proved that they have antibacterial properties. What is the advantage of it? The fiber we are using is biodegradable. The agent that we are using is biodegradable. So unlike silver, it will not stay in the environment forever. So we have, again, wound dressing is a really, really big area that is expanding. A lot of nanosilver is ending up into the environment. You can find a lot of research of the footprint that it got, and we are trying to solve that problem with a bio alternative. Similarly, once you understand how to do encapsulation, you can actually, for example, here we have used a self-assembly peptide, which when I was in Leeds, it was a patented technology of Leeds, the self-assembly peptides, P11.8. We use that to create some seriously complicated textile architectures. You can see here, we have created two kinds of fibers, one at the submicron level, the other one is at nano level, where you can actually make this fabric, you can insert it into a defective bone, and the degradation profile of this fabric will be governed by the fiber diameter of the fibers, and the self-assembly peptide will help in healing that bone. We actually did more work after the published paper, and we have tried other bioactive therapeutic molecules, APIs, to encapsulate into the fabric. And we got serious amount of first-hand knowledge now how to use that in a clinical environment. Now, instead, that knowledge, it was very difficult to work with self-assembly peptides because you don't want to destroy their molecular structure, their beta configuration when you're putting it into the fabric. But using other nanoparticles will be less complex than that. Means you can use antimicrobial agent, UV blocking agent, you can create hybrid nanoparticles, and you can start creating a family of very high application textiles. Not only for garment application, but for serious technical applications where the market is expanding at an enormous rate. I'll come back to that in a second, but what is my dream and my group's dream? We want to make healthcare stratified. What that means is, think about two people. One person's BMI is higher than the other person, maybe significantly higher. If you have a headache, if you go to the doctors, they will give 500 milligram aspirin. For the person with lower BMI, it might be toxic to them. The person with higher BMI, it might have no effect on them. So if we can use textiles to target applications, medicine to different individuals differently, that surely is the holy grail for medical treatment, and that is what we want to achieve. And I think you can link what I presented with that concept. I'm coming back to technical textiles, right? I assume the audience today is predominantly from India, and in India, technical textiles is of serious importance now. This is a document published by Indian government. India is investing $1.4 trillion in infrastructural development, and they published a document where they accepted the importance of technical textiles. The research that I presented in medical textiles, the fundamentals of that can be used for purifying water. In fact, I had a project with India to do exactly that. It can be used for horticulture. It can be used for developing infrastructure. So this is the future, according to me, for textile research. And it is really, really exciting. As I said, the biggest skill that we need to learn, apart from our subject, is how to collaborate. Now, this is a cross-section of the senior members in my team. Apart from me and another colleague, none of them are from a solid textile background. Some of them are computational chemists. Some of them are have their PhD in developing cancer drugs. Some of them are mechanical engineers. What I'm trying to do is bring all of them, as well as people from civic society, under one roof, so that we can do research which got impact. And we are collaborating with other universities as well. This is one example where University of Leeds, myself, University of Huddersfield, and Royal College of Art was granted a £5.4 million funding from the government to develop the textile industry. And we are working with now more than 360 companies, totally commercially driven. And you will be surprised that how many companies are interested in textiles. One of our partner is IBM, with whom we are developing different algorithms to understand the consumer need. And then we are informing our science accordingly. I hope I'm able to give you a picture of where textile research will go in the future, and we are really excited to share that. Thanks for the opportunity to speak here. Thank you very much.
Thank you so much, sir, for such a detailed presentation. There are questions from the participants. One of the participants, Ujjwal Mandhane, he asks, what about sustainability in medical textiles?
Sorry, yeah, see, medical textiles, it depends on sustainability. We have to get one thing, right? Sustainability is not a roadmap. Sustainability is a philosophy. Sustainability don't have any KPI associated with it. So it doesn't matter it's medical textiles or agro textiles. If you want to judge the sustainability, you have to create a circular economy model. And then you have to look at the other pillars, like the social impact and stuff like that. There are various LCA softwares that we use to define what is the sustainability of that. Nobody can answer what is the sustainability of medical textiles. It's different on what product you are developing and what product it replaces.
Yes, sir. The second question by another participant is, please give an example of innovation in textiles made using limited resources. If any example of innovations in textiles made using limited resources.
You have to define what limited resources means. Let me articulate that, right? Say, for example, you have nothing apart from a dyeing machine, right? That is a kind of good starting point. You can even say, for example, in polyester dyeing, I'm thinking loud, right? I'm not very good at it, but say in polyester dyeing, you can even work a lot to decrease the temperature in polyester dyeing. that will have huge implications for PLA dyeing, which completely destroys the structure at higher temperature, so on and so forth. And you can even do solid, meaningful research with limited resources. I will tell you one thing. Resource is never a limitation. When I joined Huddersfield, I started from scratch from Leeds. And we built it up slowly but steadily. It's all here. This is the research which really matters, nothing else.
Definitely. Thank you, sir. Thank you so much for such a wonderful presentation, sir. Once again, I thank herewith and kindly accept our appreciation of certificate of appreciation, please, sir.
Thank you very much.
Thank you. Herewith, I announce that the technical session is over. Let's start with valedictory session. We are very much interested in knowing the feedback of participants, as these feedbacks are important for us to conduct future conferences. So to start with this, first of all, I would like to request Professor Govardhan Chilkoti, who is from Vignan's Foundation for Science, Technology and Research, Guntur, India, for feedback about the conference. Please, sir.
Sir, good afternoon, one and all.
Good afternoon.
Greetings of the day. So myself, Govardhan Rao, I am working as an assistant professor in Vignan's University, Andhra Pradesh, located in Andhra Pradesh. So I am glad to tell you that the conference was very wonderful conference, which covers various types of various topics such as recent trends, innovative products and processes in the field of textiles. Okay. Mainly the speakers also, they have given very good presentations on the assigned topics, which are very relevant to the textiles field and which are very important also. And once again, I'm very thankful to the organizing committee, the Professor P.V. Kadole sir, Professor UJ Patil sir, and Professor M.Y. Gudiyavar sir, and all the organizing committee members like Rai Bagi madam and few more. So I am very thankful to the DKT Society, Textile Engineering Institute, ICHALKARANJI, for the conduction of this such a wonderful technical, innovative products and processes virtual conference. So I really enjoyed the topics which are covered in the 2 days virtual conference. I'm looking forward the most relevant topics in the future also. If any topics or any conferences are organized by the DKT societies, please inform us, so we will attend the future conferences also. So till this, once again, I would like to thank all the organizing committee members of DKTE, and as well as to give this opportunity to speak about the conference. I'm very thankful. Thank you all.
Thank you, sir. One announcement is there. I have shared the feedback link in the chat box too. So participants are requested to fill the feedback form. After successful submission of feedback by participants, certificates will be sent on the registered email ID. Now we will have next feedback by the participant, Mr. Amol Thite, who is Senior Scientific Officer at Bombay Textile Research Association, Bitra, Mumbai. Please, sir.
Thank you, madam. Good afternoon to everyone. As an alumni of this DKT, first of all, I must congratulate to them to pick up rightly the theme of this virtual conference, Innovation in Textile Products and Processes. Structurally, this conference is well organized by the DKT. As far as technological is concerned, I am very fortunate to learn the scientific excellences from the respective subject experts, specifically in the domain of this technical textile. I am most thankful to the Professor P.V. Kadole, Professor UJ Patil, and all the team members of this international conference to success this conference at the end. Thank you very much, ma'am. Thank you very much to all.
Thank you, sir. Now we request next participant, Mr. Varkha Bagwan, who is MSc Textile Engineering Research Scholar, RWTH Aachen University, Germany. I request him for the feedback speech. Please, sir.
Hello, good afternoon, everyone.
Good
I am Varkha
afternoon.
Bagwan, currently postgraduate research scholar studying at RWTH Aachen University. To start with, on the first day, we got a lot of information regarding various topics such as nanotextiles, composites, and on the topic of the sustainability also. What is the actual need of the sustainability and what are the challenges we will face during that? And today, we also got a lot of information regarding various topics such as how the textiles are useful in the pandemic to counter the pandemic and how it is saving millions of the lives. And we also got a various knowledge and scenario regarding various textile industries present in the Bangladesh and how the smart textile can be produced with the help of the biomimetic approach. And we also got an information regarding the various innovations present in the non-woven textiles and their applications. From the student point of view, I would think that these papers that have been from the yesterday, we have been seeing, provides a lot of information to all the students and it clears various aspects to all of us. I would like to thank to DKT for arranging this virtual international conference and also to the speakers who share their valuable knowledge with us and increases clear out few aspects and also increases our curiosity regarding the topics. Thank you once again.
Thank you so much, sir, for your valuable feedback. Now we will have next feedback by Mr. Dinkaran S., who is Managing Director, Sambandham Spinning Mills Limited, Salem, Tamil Nadu. Please, sir.
Good afternoon to everybody.
Good
it is
afternoon,
my
sir.
to all the participants and the papers who are presented in the international conference. It is my immense pleasure to join this international conference and providing my views and thoughts. This 2 days program was very interesting and thought-provoking, especially nanotextiles, medical textiles, technical textiles, and responsible chemical management. Today's requirement for innovation in textile products and process are not only based on sustainable fiber alone, also we need the product itself to be sustainably made, like usage of less natural resource, usage of electricity, manpower, and reducing our carbon footprint, etc. Overall, the future fashion is going to be rapid, but with the sustainability being an anchoring point. So all the technical, functional, and innovational product should have sustainable background in the process to outshine as the key universe sales point for the product. Also, all the aspiring DKTs kindly note the textile is an evergreen sunrising industry, and we need to emerge as one of the stop for all the requirements for exports and domestic requirements. As we as a nation are fastest growing economy in terms of consumption and manufacturing. Many startups in textiles are excelling with the angel investors in India and abroad. Textile being a second largest industry after agriculture, so the future is bright. This 2-day innovation textile product and process conference be an eye-opening for all the textile technocrats, and we must thank for the organizers for conducting this wonderful international program. I thank you for the opportunity given to me to share my views in the excellent platform. Thank you very much. Jai Hind.
Jai Hind, sir. Thank you so much. Thank you once again for all of your feedback. They are really valuable for us. Now it's time to move on towards vote of thanks. The vote of thanks is by Professor R.L. Gotipamul. Feeling gratitude and not expressing, it is like a wrapping a present and not giving it. So we request Professor R.L. Gotipamul of our institute for summing up and vote of thanks. Please, sir.
Am I audible?
Yes, sir.
Okay. Good afternoon to everyone. Concluding a 2-day seminar or conference can be difficult for me because after a day or more of the learnings, questions and discussions, it is hard to sum up the things in just a few minutes. But I got this opportunity to recap the main points of this virtual conference. The virtual conference, it was started from yesterday. On the first day, there were 5 speakers. On the second day today, 6 speakers. So I am here with to recap some of the points from the eminent speakers. The first presentation from the Dr. Rajesh Mishra from the JEC University of the Life Sciences Prague, JEC Republic. It was on the nanotextiles, past, present, and future. Nanoporous materials, nanocomposites, nanofibers, nanochemistry, nanotechnology. These are the major worldwide research is going on for the 21st century. It was a very wonderful paper. The second paper from the Dr. Ashok Raj Purohit from the GE Renewable Energy from India. The paper title was Fiber Reinforced Composites in the Wind Turbine Blades. Extremely research paper, very well explained on the requirements of the wind turbine blades and the properties of the carbon fiber with a sustainable environment. Very informative for high-tech research. Thank you, sir. The third paper, right, it was from the Germany of University, Dr. Nico Behrendt. His topic for the presentation was new approaches to the production, chemical modification, and the use of the smart nanofibers. He highlighted the research work on the production of the smart nanofibers, elastic modification, and the nanofibers production with the polytetrafluoroethylene, PTFE, nanoparticles. Very informative and the research article, sir. Number 4th paper, it is from the, again, from Germany, RWTH Aachen University. The paper title was on the challenges in the recycling of post-consumer textile waste. Discussed about the challenges in the recycling of post-consumer textile waste with reference to the pure input material, additives, and decolorization. A very interesting and informative paper. The last paper for the first day from the formerly GCTI, that is Uttar Pradesh, Kanpur, and Professor Dr. A.K. Patra, head of the textile department, presented and discussed the paper entitled Chemical Management in the Wet Processing, the Responsible Way. And he quoted many very informative regarding ZDHC, that is a zero discharge of the hazardous chemicals, manufacturing restricted substances list, MRSL. He further explained the GOTS certification, that is a Global Organic Textile Standards, as the latest version 6.0, covering the processing, right, manufacturing, packaging, labeling, trading, and distribution of textiles. Sir, it was a very pure technical paper. And today, second day of the conference, and we have 6 papers. Today's first session was started with the Dr. Ramakumar Sheshatri, and it's a patentable research, textiles as pandemic countermeasure. Right, he has developed a cheap, disposable, life-saving face masks in fighting the pandemic. He has been interviewed recently on major radio network in USA on this research, and he explained the practicals, that presentation with the live case studies. A very encouraging research-oriented paper. The second paper from today's session, Professor Ayub Nabi Khan from Bangladesh, and his paper was on the research and development activities in textile sector in Bangladesh, opportunities and challenges. He has briefed the textile sectors at a glance and a research scenario in Bangladesh. So it was a very excellent paper for the survey review type paper. Then the eminent professor from Hong Kong Polytechnic University, Dr. Manas Kumar Sarkar, very wide research and industry experience. He presented paper on the smart textiles or e-textiles or interactive textiles, intelligent textiles. That is the upcoming area in technical textiles. It's a breakthrough research has been done, and he explained very well all the research findings. The next paper from Sri Vinay Karulkar, BWF, India. The paper was very interesting on the non-woven needle punched felt applications in various technical and industrial applications, demonstrated practical applications, and including protective textiles for the bulletproof jackets, including the felt in a communication satellite by Indian Space Research Organization, ISRO, a very wonderful research findings. Martin Pelger from the RWTH Aachen University, Germany, is fundamental research paper on the made-spun polypore methylene pentane, PMP, alloy fibers for the gas separation applications. A very technical paper, and demonstrated all the experimental work in Japan by using two made spinning lines and using two spin rate concepts, two C-shaped spin rate and a full profile the spin rate. So this work is supported by the joint grant of the Russian Science Foundation, RSF, and Germany. Exhaustive core research from the Martin. And today's conference, the last speaker are from the is from the University of Huddersfield, UK, Director, Technical Textile Research Laboratory, Dr. Parik Goswami, described the paper Invention, Innovation, and the Value of Death. He quoted the difference between the invention and innovation, explained the commercialization process for the different applications, and he demonstrated some research case studies. A very unique paper. Now I'm moving to the vote of thanks. It seems to be a great honor to propose the vote of thanks to all who have helped us in making this conference a very resounding success. On behalf of DKT, first of all, I had like to give my hearty vote of thanks to our chief guest for keynote address, Professor Dr. R.S. Rangaswamy, HOD Department of Textiles, IIT New Delhi, for gracing virtual conference. Thank you, sir, for your very thought-provoking and interesting address. I would like to thank our distinguished 11 speakers from 7 countries, namely Professor Dr. Rajesh Mishra, Dr. Ashok Rajpurohit, Professor Dr. Nico Berend, John Thiel, Professor Dr. A.K. Patra, Professor Dr. Ramakumar Sheshadri, Professor Dr. Ayub Nabi Khan, Professor Dr. Manas Kumar Sarkar, Sri Vinay Karulkar, Martin Pelger, Professor Dr. Parik Goswami, for making an excellent presentation and making this virtual conference very meaningful and interesting. I would also like to take this opportunity to thank participants who have actively involved in this conference for last 2 days. I sincerely appreciate your attention, and also thanks to the participants for feedback about this conference. And I thank our respected director, Professor Dr. P.V. Kodole, and beloved HOD, Textile Department, Professor Dr. U.J. Patil, for their guidance and moral support. I am happy to express a vote of thanks to our dynamic professors, which are they are the part of the committee members of this conference. Those have made this conference a grand success through their hard work and dedication. Thank you all. Be safe, healthy, and happy. Thank you once again. Over to Madam.
Thank you, sir. Really, unity is a strength. When there is a teamwork and collaboration, wonderful conferences can be organized. All the textile delegates and everyone who are present now kindly have social connect with the DKT through these social medias. Now I request everyone to make their camera on so that we can capture few screenshots, please.
केलं का तुम्ही ऑन केलं
We are capturing few screenshots. Once again, we request participants to fill the feedback form. Now we have came to the end of today's session. We are all most grateful to all the participants. It's been a great pleasure. Thank you once again. And now I declare that the 2 days virtual international conference is over. Thank you one and all.